a bit later. So let's number the innovations, go to the innovations. So our setting is industry, manufacturing industry. We have factories, networks within the factories. We have supply chains that supply parts, and in some containers, you will actually see even the pictures of those containers that are also part of the network connected to the internet. I will discuss how exactly. So we have this ecosystem that has a lot of communication within a very complex networks. So our framework is built on top of that to monitor what happens in there, targeting what happens within the IoT systems. Some innovations of this framework. We'll of course go to every one of them in a bit more detail, but let's number them here. Our first encrypted means of communication, using attribute-based encryption and using also blockchain, as I said, for additional security. So the log of events of what's going on in the system are logged in the blockchain that is immutable. And all the communication between the components of the system is encrypted using certificates and PKIs and so on. We'll see. Multiple levels of machine learning. Machine learning, including deep learning, that we employ. Those methods that we employ here are meant to detect outliers and anomalies in the system. So the models are trained in using data from the real world environment in a real factory to detect attacks. That's one thing, and the other thing is maybe faults that happened in the system. So this anomaly detection happens through all the layers, as we will see, all the layers of the architecture, starting from IoT devices themselves up to all the layers into the cloud, where we have the most processing power, and methods used there use the most memory, most processing power, and they are the most powerful. So the domain is anomaly detection. The domain of usage of machine learning, deep learning, is various methods of detection of anomalies in such a complex system. Okay, then when the anomaly is detected, or fault is detected, or some error in the system is detected, then there's a question of how to mitigate. Mitigate the errors, mitigate the consequences. And for these purposes, we have a mitigation engine. So with a few components working together to provide a meaningful response to these anomalies and in minimal time. So one thing is when an error or anomaly or outlier is detected, we can inform natural intelligence, inform some administrator or monitoring officer using some visualization tools, and that's also what we do. So then the humans can take action, but the other thing is mitigation engine that would provide a response to the anomaly, typically shutting down parts of the networks where the anomaly is detected in a minimal time without the need for human intervention. Okay, another innovation is flexible anomaly detection that adaptively triggers. anomaly detection modules at different system layers. So as you will see, we also have a system. So this is not about anomaly detection itself. This is about triggering anomaly detection modules in different parts of the system, trading off accuracy and response times, and adapting the system to what actually happens, to the events that actually happened in the system. We have a component that does this. The differential private methods. This is an interesting topic. So I mentioned that we have implemented some privacy-aware machine learning methods. And just to try to explain what this does, this is a relatively novel concept. So if we wish to work with the data that contains sensitive information, both for training of the machine learning methods and inference, so we might want to use the data and use the parts that are necessary and essential for building the models, from training the models, but to use them in a way that do not disclose sensitive information that has been that's contained in the data. So that is okay, maybe training the machine learning models with the data that contains sensitive information, for instance, IDs of some persons and so on. So the method that we use is called differential privacy. It's actually a clever way of adding noise to the data. So the right amount of noise to the data so that the confidential information is masked by that noise. You cannot read it, but the features that we use to train the model are still there, are intact, so that we can use the data in a privacy-aware way to train the models, to get what we need from the data, but not to disclose the information. And we've implemented some of these models to differentially private machine learning methods. Okay, so the security level, that's what we covered, also hardware level and software level. As we will see, we designed a custom IoT edge node devices for the one of the use cases, logistics use case. So we didn't use what's available in the market. We had to build a custom devices that have all the characteristics that we need, and they're tailored to this logistics use case, and we deployed them in a real industrial environment. So in that sense, I think what I covered up until now was in the software domain, but this is where we enter hardware level security, where the chips themselves employ some security methods, cybersecurity methods that we will describe a bit later. So these devices, we will see the pictures a bit later. These devices have been designed and built within this the framework of this project. And finally, it says we developed privacy-preserving cloud-based malware analysis framework, trusted execution. It utilizes trusted execution environments, trusted execution framework, able to offload the analysis of suspicious files to the cloud confidentially. We'll see some components that do this too. Okay, we discussed, I mentioned the two use cases. Now we need to discuss them and to describe what actually goes on within them. So there are two real-life experiments provided by the use case provider, CRF. In this case, that's in automotive sector. And okay, maybe the first one is what we call inbound logistics or smart logistics or logistics 4.0. So we can imagine having multiple factories that have parts coming in from the supply network that is worldwide, and those parts travel in containers. In some containers that we will, I think there's a picture a bit later, and we would need to track every one of those containers. What happens with every one of those containers in real time? So that's why we call it smart logistics or inbound logistics, since we want to monitor this, but not only to monitor what happens in a means of transport or warehouses where these containers are stored. We also want to aggregate the data and run some machine learning algorithms to see if there are some anomalies, if there are some events that we do not consider normal. So that there's this cybersecurity part. So the system manages different parts from many origin points that come to the manufacturing plants. And of course, IoT is the key technology here to enable the optimization. So I already mentioned that we custom built some IoT devices, and those are used actually in this inbound logistics use case. There's some microcontrollers, something like a relatively powerful Arduino or microcontroller with certain modules added to it that we attach to every container. So every container in the system has this device. They are low-cost devices, has this device attached to it, and this device tracks monitors, has various kinds of sensor, tracks what happens with the container and transmits the data. So they're all connected to a network, transmits the data using relatively innovative NB-IoT, narrowband IoT technology through mobile network onto the upper layers of the system. So we have in this way, in this use case, we have a real-time monitoring of what happens with each container in the supply chain. The container can be, those devices have batteries that last a very long time. So they're independent of any source of power. So since the container can be loaded onto a truck or, I don't know, ship, or it can be stored in a warehouse. But it does not need additional power. The second, so that's the first use case. We will of course go through the architecture of it a bit deeper and explain how it works. The second is the so-called smart factory use case. In this case, we have machines on the plant floor. So it's in the factory. This everything in this use case happens within the factory, And we have some data from the machines that are on the plant floor. They're AGVs, automatically guided vehicles. So there are some vehicles that do not have a driver. They're automatically guided on the shop floor. IoT devices attached to these AGVs, and they monitor what happens with them, collect the data feed them into the upper layers. It says here, sends the data to the cloud. But in this case, we use different IoT devices, since in this case, the first difference is that we are within the factory, inside the factory, so that we don't have to use a mobile network to connect to the rest of the network. We can use Wi-Fi, for example, or in case of robots, welding robots that are not moving around, we can even use wired network, Ethernet network. And the other thing is we can use IoT devices that have that are much more powerful and have much more storage, since we do not depend on batteries for the power. We're inside the factory, so we can connect them to the power source. And then it seemed logical to use more powerful devices, and in our case, those are Raspberry Pis. So Raspberry Pis have much more storage and have much more processing power comparing to those edge node devices used in the logistics use case that are microcontrollers. So we have Raspberry Pis attached to these devices in the factory, sending the data, monitoring what happens, sending the data through the Wi-Fi or even Ethernet to the factory network. And that then provides real-time management of what goes on. And of course, since our domain is cybersecurity, that enables us to monitor any events that we consider anomalous. So we use the methods that I already described, and I can describe a bit in a bit more detail to detect anomalous events, and not only to detect, but also to mitigate the consequences. So the mitigation engine is actually applied in this smart factory use case, since it can using Sdn controller, it can manage what happens in a factory network. So then it makes sense to mitigate the consequences in this way. And in inbound logistics use case, we have some containers out there in the mobile networks, so we don't have that kind of control. So the actual mitigation engine is what we also have in a smart factory use case. Having said all that, more or less as an introduction for this slide that we see here. So this is the final architecture of the system, and I would like to go through this architecture with you, describe the data flow, not in too much detail, but describe what goes on here, and then after that we can maybe concentrate on some components that are maybe more interesting than others. So what goes on here, how to even start considering what happens in this picture? Well, we can first see that there are three layers of the architecture here. So the first layer, I don't know which one is the first, the lowest layer of the architecture is the edge node layer. You see it here. With IoT devices, trucks, warehouses for the logistics use case, and Raspberry Pis for the smart factory use case. So this is what happens in the edge. We will describe data flow in a moment. On top of that, we have a field gateway layer. So these are layers where we have more processing power. This is within the factory network or within the mobile operator network, where we can have servers and we can run more complex methods. There's also this Sdn controller that I mentioned here in the field gateway layer, and the upper layer is the cloud. So this is the cloud layer. It seems that this title should have been somewhere up here, but it's covered by some other component. But this is it. So these are the boundaries of the cloud layer. So that's what happens in the cloud. So these are layers, what we call layers of architecture, and they are what we already described. Now you can see that there are a bunch of components within those layers, but there's also here in the left side of this picture, there are levels that are actually not the same as layers. There's another picture describing the levels. Yeah, it's this one, where you can actually see that each consecutive layer contains what's physically in the layer before it. The physical dimension being these layers, edge, field, and cloud, and levels being something else, but in the physical sense, the consecutive layer contains what has been in the previous layer. And in this, I will go back to this picture since I think it's more informative. We have first level is hardware-enabled security. We mentioned that we cover both software level, hardware level security. There we have provided by Infineon Optica Trust M modules, and this is hardware. These are chips that provide hardware-enabled security. And we have also belonging to this level, first level hardware-enabled security, the IoT devices that I already described. So in this logistics use case, there are microcontrollers. In smart factory use case, there are more powerful Raspberry Pis. In the second level, security by horizontal device-to-device communication. So this is what happened between devices. And here we have, as I mentioned, the communication between devices and between the components is encrypted. This is attribute-based encryption, and everything, events that happen in the system are logged in the blockchain. And this is what we call decentralized access control. And there's also the traffic analysis module that can analyze the traffic even though it's encrypted. So that's what happens in the communication between devices. And the third level is security by machine learning based behavioral analysis and cognitive security capabilities. Now this is beyond this security in the communication of devices. It says behavioral analysis and cognitive security. That's actually what we call BACS, BACS component that goes through all the layers of the system, and that enables, well, monitoring of what goes on in the system as a whole, and detecting anomalies, detecting flows, detecting errors of the communication. It says, yeah, so this module is not a component. It's actually put here, that component. But as I will describe a bit later, we have methods for anomaly detection through all the layers. It operates through all the layers. So let's consider then, using this picture, let's consider what happens what would be the data flow in a, for instance, logistics use case. So within trucks and warehouses attached to the containers, we have, I think I have, yes, a picture here. Those are the edge node devices for the logistics use case. You see that there are small boards with various kinds of sensors attached to them. They also contain a SIM card, since they needed to communicate on the mobile network. So there's a SIM card. They communicate with mobile network using narrowband IoT. That's a relatively novel technology for these purposes. And the casing, you see, these cases have also been developed here in Novi Sad. They're much bigger than these, the SIM redundant, much bigger than these plates, since below the board there's a battery, and the battery needs to be a larger one so it can last for months. It's actually, the idea is for the battery to last at least 2 months, rechargeable batteries. So that's why the containers are a bit bigger. And then you can imagine these devices, so they're completely they don't depend on any power sources or any infrastructure in terms of Wi-Fi networks and so on. Since we have coverage for NB-IoT in the area where we tested, they only depend on mobile network operator. Okay, they depend on someone who needs to recharge the batteries every now and then, but as I said, they last for at least 2 months. So these devices are not in constant. Sorry. No, now I made a mistake. So if I play from current slide, okay. And then you can, I think in the next slide you can see those devices. Okay, in this picture the casing is a bit different, but using the same casing, they're attached to these containers that are used for the transport of the parts that you can see here.
I'm sorry, we can't see your slides right now.
Sorry, I will. For some reason I stopped sharing. Is it better now?
Yes.
Okay. So okay, you can see the containers here, and the devices are attached to each container like this, and the containers that are then either in the warehouse, as they are here in this picture, in some warehouse, or loaded to some vehicles and being transported here and there. In our experiments, they went from Torino to Budapest and back, and so within the trucks. Now you can. So this is actually how this looks. Now you can imagine this is a maybe similar picture as before, but with a bit more detail. So this is what we have in the edge node in trucks and warehouses, microcontrollers within the containers. And the container itself, within its firmware, has some libraries, has a functionality implemented in C programming language from scratch without using any libraries to process the data even at the edge, even though the microcontrollers are not have low processing power. There's actually a neural network autoencoder with one hidden layer running on each of those microcontrollers. They have been pre-trained with real world data, and we have, so in this sense, we have anomaly detection even within those devices that we've designed within their firmware. That's, as far as we know, innovative method. So this anomaly detection is relatively weak. It's an autoencoder with one hidden layer, not too big. So what it cannot process, it will send to the upper layers. So in the upper layers, up here in the field gateway layer, so the data is sent to the mobile network. We have servers, much more powerful devices, running other methods for anomaly detection. There are I think at least 20 of them. Some run here at the field gateway level, and some run at the cloud level. Some of them are more powerful neural networks, like recurrent neural networks. Some of them we use Facebook Prophet, and we use traditional machine learning methods for anomaly detection. But there's this tool that I mentioned that's flexible, that enables flexible anomaly detection and adapts to what goes on in the system, security-aware dynamic offloading decision mechanism, that using the scores from the anomaly detection in the layers below it and in this layer decides if there's a need to offload the data for further analysis to the cloud, or if the analysis can be constrained to the field gateway level. So it only decides, and if it decides that a further analysis is needed, then the data is sent to even upper layers to the cloud. And then when so this is actually similar in the smart factory use case. We can deal with the cloud later. In the smart factory use case, we have a similar thing, but in this case, I think I have a picture here. So this is a Raspberry Pi device, much more powerful. With I think they're with 520 megabytes of RAM, and with some ARM processor, but much more powerful than the one in the microcontrollers, and they're attached to the AGVs. This is an AGV, automatically guided vehicle. So those are the vehicles that operate on the shop floor, and there are various kinds of sensors on those devices that monitor what happens there. You can imagine Raspberry Pi connected to one of these, and also connected using Wi-Fi to the factory network. And then it feeds the data for there are all kinds of sensors, feeds the data to the upper layers. As in this, okay. Similarly to what happens in the logistics use case, there's some anomaly detection within the Raspberry Pis themselves, since they are more powerful than than those methods are more powerful than in a logistics use case. But in a similar way, the data is fed up to the field gateway level, where we have servers where they're much more powerful, And if the Medici tool says that additional processing is needed, then the data is offloaded to the cloud. There are GPUs, and so even more powerful devices and neural networks, and not only neural network, but other methods for anomaly detection. So that's kind of a data flow from the ground up to the cloud level in both of these use cases. And now when the anomaly is detected, well, the one thing is to alert this user using, I don't know if I have a problem with this small window, using advanced visualization. So that's a GUI, something like a GUI of that the humans can use for the whole system. And the other thing is, of course, the mitigation engine. You can see it here. So this all happens in the cloud. The anomaly is detected. The info about the anomaly, the data, where it happened, how it happened, goes to the mitigation engine through security assurance module. So there's this component called karmas. That's a curious component, a very interesting component that's actually used in France for controlling the levels of water in the rivers, and it's able to detect the problems and using floodgates to mitigate the problems within the river network of the France. So it's actually similar. That's similar. What goes on here is it can detect the optimal way to mitigate the consequence of anomaly, of an error that happened, so that it shuts parts of the networks using the Sdn controller. And that's the mitigation engine. That's the response fed down to the layers below. Field gateway layer that's within the network within the factory. For logistics use case, there's also this some kind of mitigation BinSec module that continuously verifies the firmware of the devices, of those IoT devices, and it can detect problems. So if they're tampered, so the device can be tampered by changing its firmware. If that happens, then this can also be detected. Okay. Yeah, we went through the pictures. I explained what happens here. We did okay. What we didn't mention, maybe, yeah, that's something I should add and maybe wrap up. Is the communication. The communication goes on through streaming APIs using Apache Kafka with certificates. So the communication is encrypted using certificates, and certificates are issued by the identity management module, PKI. So there's in the cloud there's a server for these purposes. So the system has this this issue covered in that way. We don't see the Kafka and the actual means of communication here in this picture. Is we only see the arrows, but what goes on, the data being exchanged between the components are changed in this way, encrypted using certificates, using streaming APIs, certificates being issued by the central certificate authority running in the cloud. And yeah, some checking the time. Yes. So that's the we could of course go into details and about this or that components, but that's some kind of a bird view of the architecture of the system. And that covers the goals, the objectives of the project, and covers what we mentioned in the project statement. Yeah. Since I have only 8 minutes left, then I would stop here and maybe take some questions.
Okay, thank you so much for that very interesting presentation. So, of course, we can now take any questions that are in the audience.
I can maybe go back to this picture. Yeah.
Hello, good morning.
Good morning.
Good morning. I'm Sharunida from University Kuala Lumpur. Could you explain a little bit on the role of blockchain in your layer 2 system? From my understanding, the blockchain role here is just to authenticate the sensors. Is it correct?
Okay. One thing is authentication, but the other thing is so whatever happens in the system in all layers and in all devices is logged in the blockchain. That's immutable. So that's the idea, to have the immutable log of events in the system.
So meaning that all the event will be logged in the blockchain.
Yes, yes.
So how about the scalability? Scalability, because if all the events are logged, there are a lot of sensors, a lot of events. How about the scalability of the blockchain itself?
Scalability. Well, the blockchain, I imagine it's distributed. You think that it would be clogged with the overwhelming amount of data?
Because I think that because if all the data are logged, meaning that all the transaction, all the information being logged,
yes,
it might have scalability issue in the future, because IoT data is millions of devices.
Mm-hmm.
Yeah, billions it can be. Yeah,
yeah, we didn't consider that issue, but yeah, okay. So some information for what happens in the IoT devices is written there. But yeah, I couldn't imagine that we could clog the blockchain in this sense. It's distributed by
yeah,
itself.
yeah.
Yeah. So yeah, we didn't consider that. That's unknown to me.
Hello.
Yes.
Yes. Good morning.
Good morning.
I'm Kosigan from University of Lomé in Togo, West Africa. I have to know, according to risk assessment module, what kind of risk assessment method are you using? That is the first question. And the second one,
I didn't get that. I didn't get this question. What? Can you?
kind of? Yes. I want to know what kind of risk assessment method are you using?
Risk assessment methods.
Yes, risk assessment method. And the second question is, do you integrate a kind of resilience strategy in your architecture? In case of if we have a kind of attack, because we are talking about cyber security. So if you have an attack, what kind of resilience method are you using, or if you integrate a kind of strategy? This is the true question. Thank you.
Okay, yeah, we can. For the risk assessment, it's difficult to go into that. That's described. I can maybe point you to the website of the project where you can find deliverables, and within those deliverables, we did a risk assessment analysis, numbering all kinds of threats, and the responses to those threats that the system can detect, and that's quite a comprehensive table that you can find in the documentation, but it's difficult to discuss them now. And for resilience strategy, it's so well. Actually, all this talk about how the system works sounds like it's pointed in the direction of resilience. So yeah, for instance, resilience of the system to various kinds of attacks covered by different functionalities that I have described. So that's it. The functionalities of the whole system are actually pointed in this way. There's no strategy beyond that. So system is resilient in some way for attacks in this way, so that if an attack has been detected by the methods that I described, we have a response. One thing is alarm for the humans, and the other thing is a mitigation engine that tries to, in different ways, to make the system resilient. So, I beyond that, we didn't consider it as a strategy.
Okay, thank you very much.
Okay.
Okay, well, thank you so much for the presentation. I think it's time for our next presentation, but thank you very much again.
Okay, thanks.
So now we're going to be moving on to our next presentation called Information Security Risk Management and Standardization on IoT Cybersecurity by Hervé Cholet of the Luxembourg Institute of Science and Technology. So I welcome now Hervé to begin sharing his screen and test out his sound.
Yes, thank you, Camilo. We try to share my screen. Okay, good morning, everyone. I hope you hear me correctly and you see my screen.
Everything is perfect, so go ahead.
Okay, perfect, thank you. So I'm Hervé Cholet, and I have been working as a researcher at least for more than 10 years now. And I will present you today a talk on the information security risk management and standardization on IoT. So it will be a quite high-level view on cybersecurity, and a more technical presentation will occur just after me with my colleague Buen Liu. So this is the agenda. And let's start with a short introduction and a presentation of the list. So LIST stands for Luxembourg Institute of Science and Technology, and you are situated at the heart of Europe. And we are, for example, at 1 hour from Paris. And as you can see, there is not only banks in Luxembourg, there are also research centers. We are active in a lot of different research domains, and we are mainly active in 4 fields. the environment, the informatics, the materials, and the space. And so maybe I will disappoint some of you, but for IoT security, as for every domain, there is no magic list of technical security controls that you can implement. It is also important to obtain a proper cost-benefit balance, and this is why a security risk management methodology alimented by standards are useful and is useful and needed. And thus, we will have here an overview of the information security risk management before seeing just after the standardization on IoT. So, first of all, what is a risk in general? So it's always interesting to exchange, brainstorm a bit on this word, on this definition. But of course, the format of today is not easy for that. So I will give you directly some classical good answers. So a risk is often defined as exposure to danger, possibility that something unpleasant will happen, or possibility of harm or damage. So we have here the main keywords. And this is for a risk in general. In information security, we will try to reduce the number and the scale of impacts. And thus, the aim here is to prevent the occurrence of impacts and to mitigate their consequences. And of course, security generally leads to substantial cost. And it is not possible to address all the weaknesses. It is impossible to be fully secure. That's impossible. So therefore, it is essential to tackle in priority weaknesses that can lead to critical or significant impact. We must identify, classify, order the security risk, and make choice. So clearly, there is a concept of priority in risk management. Before to put in place a quite concrete treatment plan, and that's why a risk management approach is useful for identify existing risk, analyze existing risk, evaluate existing risk, and propose treatments. The security risk management approach is the best way to have a clear, structured, and orderly identification of risk. So here you have the main objectives of a security risk management approach. So of course, it helps to improve information security. It's the main objective. It also helps to better select security measures. It helps to justify information security budget allocation. It helps to improve return on security investment, and it helps to prove the credibility of the system thanks to the risk analysis. So after the generic definition of a risk that we have seen before, we have now the definition of a risk for the risk management world. So a risk here is defined as the combination of the probability of an event and its consequence. So here you have clearly two important components of a risk, an event and a consequence. And we can also notice that in this definition, that a risk is not only negative. For example, if you win at the lottery, it's an event followed by a consequence. And now the ISO 27005 gives us a more detailed definition for an information security risk. A risk in the information security domain is defined as the potential that a given thread will exploit vulnerabilities of an asset or group of assets and thereby cause harm to the organization. But it is totally compatible with the previous definition, since it is noted that it can be measured in terms of a combination of the likelihood of an event and its consequences. So we find again our two components here of a risk, an event, and consequence. It is here more clearly explained. A threat and a vulnerability are the event, and the threat that exploits the vulnerability is the event, and the impact is the consequence. So in details now, a vulnerability is intrinsic to the object or the situation. A threat is the probability of occurrence of an event exploiting the vulnerability. And again, an impact is the consequence. So let's take an example of the daily life, a burglary. In this case, the vulnerability may be your home keys under your carpet, or maybe a window left open. And the threat is the burglar that comes along. The impact will be a loss of money, a loss of equipment, and of course also psychological impacts and so on. And an interesting thing here is that you can see that it's difficult to modify the impact. You can try to have less money in your house, less money under your bed, for example. But it's possible, but not easy to reduce the impact. It's nearly impossible to modify the thread. The thread is external, and if a burglar has spotted your house, your home, there is nothing you can do about it. But actually, it's not totally impossible to modify the thread. You can modify the thread a bit. And for instance, if you live near a river, the threat of flooding is quite high. And if you decide to move in a desert, of course the threat will be lower. But it often implies drastic solutions. And however, you can easily modify the level of vulnerability by closing your door, by closing your windows, by installing an alarm, and so on. Again, here we have the different components of an information security risk. We have a thread that exploits a vulnerability that is a characteristic of an asset, and this will cause an impact. Here we have another term, the asset. We will define it later on. And here I repeat some information, of course. Again, the thread, the vulnerabilities, impact, but if you understand this slide, you are nearly an expert in information security, so it's really important to well understand this slide and these different concepts. So to manage this, this information security risk, we use a risk management process. And in this domain, the standard ISO 27005 is clearly the reference. The ISO 27005 is a standard providing guidelines about how to do risk management, and particularly, but not only, in the frame of establishing an information security management system in the frame of the ISO 27001. This international standard is relevant to managers and staff concerned with the information security risk management within an organization. And of course, where appropriate for external parties supporting such activities. So ISO 27005 is based on a lot of different previous initiatives, and it was initially published in 2008. It was revised 2 times in 2011 and 2018, and a new version is under development now and is expected at the end of this year. It's an international standard based on a consensus, and this standard is largely used around the world. It's not the case of all standards, but this one is really interesting. It really fits to the industrial needs, and it's not at a too high or too low level. It's really interesting. The framework is sufficiently generic, with specific examples and with several knowledge bases. So here, this is the full overview of the ISO 27005 risk management process. And it is briefly composed of the context establishment step, the risk assessment step, with the risk identification, the risk analysis, the risk evaluation. There is also the risk treatment step and the risk acceptation step. There are also 2 continuous steps at left and right, so with the risk communication and the risk monitoring. And of course, it is an iterative process. It should be regularly updated, and usually it's done on an annual basis. So the main objectives of the ISO 27005 are to detail how to conduct an information security risk assessment and treatment, to give a generic risk management methodology for information security, and like I said previously, it is of course compliant with the well-known standard ISO 27001 and allows to obtain the information security certification. And it is based on the kind of PDCA approach. And again, it is an iterative process. It's not a one-shot approach. So we will have an overview now of the main risk management concepts. And you have now the definition of an asset that you have seen previously. So an asset is anything that has value to the organization. So it's a quite large definition. But something important here is that the assets are classified in 2 categories. The primary assets that are the core activities of the organization, the services, the processes, or the products, or even the information. And you have also the supporting assets that may be mainly in the category of hardware, software, network, personnel or site. And the security risk will be analyzed on the primary assets by taking into account the supporting asset. We do not analyze the risk on a computer, for example, but on the information that it contains, taking into account that the fact that this information can be found on different computers, on some papers maybe, on one server, and so on. For example, a computer used only to give presentations will not be protected in the same way as a computer used to develop a sensitive application. So the threads now. A thread is the potential cause of an unwanted incident, which may result in harm to a system or organization. And the source of a thread can be accidental, deliberate, or environmental. And the Annex C of the ISO 27005 provides an example list of 33 generic threads. And it is, of course, useful. So this is the current list of threads provided by the ISO 27005. And as you can see, threads are in a quite high level, and it can be of very various type. You have technical failure, of course. You have compromise of information, but also natural events, for instance. The vulnerability is defined as the weakness of an asset or control that can be exploited by a threat. And the Annex D, again, of the ISO 27005 provides an example list of assets and their related vulnerabilities. We have here some example of vulnerabilities. So, after the identification of threats and vulnerabilities, we should assess their level. And for this purpose, we need to define some specific scales. And here you have an example of very generic scales used for the threats assessments and the vulnerabilities assessments. Okay, now the impact. So an impact is defined as an adverse change to the level of business objectives achieved. In information security, we only consider the negative impact, such as damage or loss, not the positive impact. It's not interesting for us. And in information security, the criteria used to assess the impact are usually the confidentiality, the integrity, and the availability. But of course, you can use anything you want, such as financial criteria or reputation criteria, for example. And so here again, you have an example of a very generic scale used for the impact evaluation. And it is important to have a clear differentiation between levels without any interpretation ambiguity, to try to better evaluate if it's the level 1 or level 2 or level 3 and avoid any ambiguity. Okay, so we have now identified and evaluated all components of a risk, since the risk is the concatenation of the cause, the risk, and its consequences. And as you remember, a risk is the combination of threats, vulnerability, and impact. Thus, with a formula, you can combine all of this and calculate the level of your risk. Here you have an example of some risk. So it's a bit more complicated that I have explained to you, but you have some primary assets, you have some thread, the thread level, you have some vulnerability, with sometimes more vulnerabilities, several vulnerabilities for one thread. You have the existing controls and the level of actual vulnerability, and all of this information can lead to a level of risk at the end of the table. So the levels of risk that you have obtained should be compared again against the acceptable level of risk. This acceptable level of risk must be defined specifically for the company by taking into account all the specificities, and it must be validated by the top management. It's really important to pay attention to this risk acceptation level. However, even if the risk is automatically considered as acceptable, you should sometimes consider some other risk, even if it's acceptable. And it is particularly the case for extreme risk, such as the risk with low impact but really high likelihood, or risk with really high impact but low likelihood. Sometimes it will be automatically calculated as acceptable, but you need to check it and check if you want to take this really high impact, even if the likelihood is really low. So once we have calculated the level of risk, we must treat the risk. And for that, there is 4 treatment options. The first one, the modification. So it basically consists in reducing the risk by implementing some controls. The second option is the retention option. And here, we decide to simply accept the risk. We keep the risk without further action. The third option is avoidance, and it is specific to some risk that are considered too high or with a cost of implementation too high, and other risk treatment options exceed the benefits. So we want to avoid this risk completely by withdrawing a full set of activities or a complete process, or avoid to develop totally a product because all risks are too high for the company. And the sharing treatment options consist in subcontracting some activities for your IT management, for example, or by taking some insurance to limit the impact. However, this treatment option can be tricky because risk sharing can create new risk or modify the existing identified risk. So here we have some classical example of IoT risk, and so now maybe I guess you are expert in information security, so you can clearly notify that there is no risk in this list. Actually, there are mainly vulnerabilities, and for example, the lack of encryption is indeed a vulnerability, and it may not be relevant in your case. It depends of a lot of things. It depends of the different threads. It depends of the different impacts. And of course, the other vulnerabilities or controls in place. So lack of encryption alone means nothing. One vulnerability alone means nothing. You must have to obtain the complete view of the risk, as well as the complete view of all the risk to assess the relevance of taking a corrective action or not. So now let's switch to the standardization on IoT. You have here quite complex diagram, and it's not relevant to explain it in detail. This diagram explains the general organization of the ISO standardization. You have technical committees, subcommittees, working groups, participative members, observatory members, and so on. But it's not really relevant here. If I show you this, it's to explain to you that you can actively participate in the standardization and contribute to the development of standards, of some standards. If you are expert in one domain, do not hesitate to apply, to participate to the development of standards. It's really open, the cost is low, and the benefits are quite huge. You can participate in the decisions, you can anticipate the modification of standards, you can exchange with experts. That's really interesting. I'm personally involved in the subcommittee 27 related to the information security, which is responsible to develop ISO standard, as for example the ISO 27005. We're responsible to develop the standard in the ISO 27 family. And again, it's really interesting activity, so do not hesitate. And as you can see on this slide, one country is one vote. So therefore, the Luxembourg has the same voice as Russia, has the same voice than United States or even France. If you participate on the ISO standardization, it is interesting for you personally, of course, for your company, and for the global community. You can share your experience to the community, and of course you spend some time on it, but you have access to high-level knowledge with other international experts. You have also an early access to all documents and draft projects, and you will be able to take part in future standards and better understand the different choices in standards. And it also gives to your company a voice in the development of standards. So here you have a list of some ISO standards related to the IoT. So it may be relevant for you for some of these standards. You have some generic topics as vocabulary, IoT use cases, reference architecture in IoT, interoperability for IoT systems. You can note also that a trustworthiness framework is under development. You have again some other standards on real-time IoT framework, for example, industrial IoT, And you have also really specific standards on underwater communication, on socialized IoT systems, and so on. And all these standards are developed by the subcommittee 41, 41, yes, on Internet of Things and Digital Twin. And it doesn't really address the IoT security. It's more on the Internet of Things generally. However, in the subcommittee 27, we have 3 standards under development. The last 2 standards, the ISO 27403 and the ISO 27402, are quite specific and at an early stage of development. But the first one, the ISO 27400, on guidelines for IoT security and privacy, is very promising. It will be the first ISO standard on IoT cybersecurity. And for this one, it is currently at the final draft stage. So I guess it will be published in 1 month or 2. So I can't give a lot of information about this standard that are still under development, but the main parts will be on IoT concepts, on risk sources for IoT systems, and security and privacy controls. So it will be a kind of useful knowledge base to feed, again, the security and risk management with specific vulnerabilities, threats, and controls. However, it's not a full and comprehensive standard, or it will be not a full or comprehensive standard on IoT security. It will be a good start, let's say, a good start for this standard. Okay, in the United States, they have also the NIST organization that publish standards, and they have the NIST Cybersecurity for IoT program that fostering cybersecurity for device and data in the IoT ecosystem across industry sectors and at scale. Here you have an overview of all standards and documents that are published by the NIST Cybersecurity for IoT program. There are a lot of interesting documents. It's of course from the United States, but you can find some lot of interesting information. In Europe, you have the ETSI organization that publish a standard for Europe, and they have published a standard on cybersecurity for consumer, Internet of Things. So it's quite specific and for consumer. And the ENISA organization, again, it's an European organization. The ENISA has published guidelines for securing the Internet of Things, but it's dedicated on the supply chain. And regarding the security certification, I think the most suitable for IoT product is the ISO 15408 on evaluation criteria for IT security that we usually call the common criteria. This is a framework dedicated for IT security evaluation and certification. So it allows to validate that a particular product satisfies a defined set of security requirements. But it is quite difficult and complex and expensive also to implement this standard, to implement the common criteria, and to obtain the certification. And here you have just to have an overview of one scale used by the common criteria. It is one scale to evaluate the assurance level on 7 level. So to conclude, if you want to develop a secure IoT product or secure IoT service, it is clearly necessary to use a security risk management methodology to define your own specific risk, because again, unfortunately, it's not possible to have a simple IoT security checklist. And it is also really interesting to take existing standards into account and to take it not as a constraint, but as a useful source of information to augment your risk management and to have a full overview of the different threats, vulnerabilities, and controls. So thank you for your attention. I will be happy to answer to your questions because we have a lot of free times for it now.
Great, thank you so much for the presentation. So please, if anybody has any questions, go ahead and open your mic.
Hi, this is Jacques Robin here. I do have a question. You presented, do you hear me, everyone?
Yes, yes.
Yes, so you presented quite a long list of standards. It's pretty impressive and daunting at the same time. And my question is, in which kind of industry conformance to such standards is a requirement to be able to put the product on the market, as opposed to just having a nice label to convince customer that you're doing the right thing?
In this list of standards, nothing is required. It's not like the ISO 9001 or the ISO 27001 that you can certify or assure some level of have a level of assurance in security or in other topics, except as the common criteria that I have presented briefly here. Here, clearly, you can have an assurance level and present it to your customers, to your client, to your partner. And this one is the only standard that you can use to evaluate and to certify in a way your security. For the long previous list, this one, you can use it as a source of information to build your IoT product, your IoT service, to have a lot of good information. But you can't really use one of these standards to prove something to your client or partners.
Okay, and even the common criteria is not a legal requirement?
No.
Okay.
On this list, there is no legal requirements. It's only standards, certification for the common criteria, but there is no legal requirements. Even again for the most well-known standard, the ISO 9001 or the ISO 27001, the ISO 14001. Maybe it's the most well-known standard. It's never a legal requirements. It may be requirements of your partners, for example.
Mm-hmm.
Maybe if you develop an IoT product for the NASA, then maybe there'll be an IoT product for NASA. Maybe. I don't know if it's a good example, but maybe they will ask you to reach the level 6 of the common criteria. That can be requirements, but it's only a requirements between partners, not a legal requirements.
Okay, and since I'm here, I have another question. Are there any standard to help you measure the impact of security on safety for cyber physical systems?
What do you mean by cyber?
Well, I mean, like when a cyber physical system where you have some software that drive, for example, an effector, or that can have an impact not only in the virtual world but on the physical world, like an autonomous car, for example, or a robot in a factory. So if the robot is hacked, then it can destroy the factory or injure the workers. Since for safety there are, as far as I understand, there are legal requirements to show the safety of your product in some industries before you are allowed to deploy them. So for a cyber physical system, is there some standard or guidelines that help you check that security vulnerability might not have a safety consequence, not just availability, confidentiality, and integrity, but safety impact?
Okay. So I'm not sure because I'm not an expert on safety or on information security, and so I guess there is some standard dedicated on safety, but it's really dedicated on safety, and I don't know if it's really linked to such a risk management, for example, and obtain a risk management dedicated for safety. I'm not sure that you have such a standard, but the ISO 27005 methodology can make this with no problem, because like I said, of course, there is the common criteria in security that are confidentiality, integrity, availability, but you can use as you want. You can analyze the risk with threat, vulnerabilities, impact, controls, and have the property as impact, as safety, as vital risk for people, vital risk for society, for the organization. You can take the property as you want. There is no problem. The methodology is perfectly fit with all properties, and you can take properties like the risk management, the ISO standard 31000 on risk management. It's really near the standard 27005. You can use it also. You can make a risk management and have the property of vital risk, of reputational risk, of operational risk, of legal risk, of financial risk, and so on.
Okay, great. Thank you very much.
Thank you.
Hello.
Hello.
Thank you. It's Kosiga from Togo, Domain. And I want to know, in your standard list, do you have a standard according to IoT in smart grid, and especially in microgrids of renewable energies? Thank you.
Yeah, so I guess no. Yeah, I don't know. I don't know all of
Or
this.
something close, or maybe some standard close to it, close to a smart grid area or microgrid area.
Yeah, smart grid and IoT, you mean?
Yeah, yeah, yeah.
Yeah. No, I don't think so. So again, I don't know well all of this standard. I'm more expert in the 27 or something standard, not on this kind of standard on generic IoT. Here, it's not dedicated standard on security. It's standard on IoT in general. And as you can see, there is no specific standard on smart grid. But this is the list of the ISO standards, and you can use maybe some other standards, maybe in the list of NIST. Maybe they talk about smart grid here. I don't know. But from what I know, no, there is no. I don't know standard that address these topics, smart grid and IoT.
Thank you. Thank you.
Hello, everyone, and welcome back. It's been, I think, our 10 minutes. So if Bowen is ready, I think we can begin to continue with the next presentation, which is called Multi-Factor Authentication and Key Exchange by Bowen Liu from the Luxembourg Institute of Science and Technology again. So the floor is yours, Bowen.
Okay, I'm gonna share my screen, but well, just one moment. Let's share up. Can you guys see my screen right now?
Yes, we can see it.
Excellent. Okay, I gonna start my presentation. So hello everyone, welcome to the Spring School of Cybersecurity for Industrial Internet of Things. Well, in this presentation, in this session, I will talk about the multi-factor authentication and key exchange for IoT. I'm Bowen from Luxembourg Institute of Science and Technology. And today, we will have 4 major chapters, and we will start with the authentication. So regarding the keyword authentication, what is the first thought coming up from your mind? And from my side, it is a daily login and connection action. This is a screenshot from the Post Luxembourg. The Luxembourg Post offers several online services like stamp purchase, which is a very critical service. However, as you see from the screenshot, the website only requires username and password. Why it is not secure? Because the password is very likely to be compromised, and then all the information stored in the website is leaked. So here I list the several common attacks to steal your password. For example, the phishing. One day you receive an email saying that your health card, in French is the carte vitale, need to be renewed, and you just click the website and type your information and your password. Then all the information, all the personal information is sent to the adversary, the attacker or the hacker. Another example is that if your password is not too long and includes some keywords like your name, your personal information, your phone numbers, your birth date, it is possible to quick fix your password within short time. Here we can see it is a news published almost 3 weeks ago. Apple, Google, and Microsoft want to eliminate the password. if you are an iPhone user, you can check the full release note of the iOS 15.5. You can find some clue in it. And if you watch the Google I/O conference 2 weeks ago, they also mentioned this feature in their future directions. How it works? In short, instead of asking you to input a password, they will request your fingerprint or your facial verifications with your phone or with your smartwatch, etc. So, if we cannot use our password, what can be used as an authentication factors? Here, I list the 4 main categories of authentication factors. The first one is something you know, something like password or personal identification numbers, which is PIN. And second is something you have. It is like some cryptographic identification device or some token. The third one is something you are, which is your biometric information. And the last one is someone you know. For example, when you forget your password, some social media request your contact friends to send some specific verification code so as to let you to reset your password. Here you can say it is a short version of how the one-time password works. Once the user wants to log in and the request consent to the server, and based on the database and based on the secret shared at the registration phase, both user and server are gonna generate a cryptographic hash based on the timestamp and the secret. And at the final stage, the server gonna compare if the user's hash value is matched with the hash value generated on the server side. If yes, okay, the user can log in. Okay, now that what is the authentication factors for IoT scenario? Well, it's the same. I mean, it's the same categories as the general case. We also have 4 categories: something you know, something you have, something you are, and someone you know. But since for some IoT scenario that we don't have the human beings involved, there's only IoT and the server communicated between each other, which is a common scenario in the industrial IoT. So in that case, we can use the device fingerprint, which is the MAC address of the device, the IP address of the device, and also we can use the behavior patterns of the device. For example, an IoT only send, let's say, only have data transmissions in the daytime. Okay, once there's some data transmission during the nighttime, and the server gonna detect that and to be treated as the unexpected behavior. So it could be some activities from hacker. And the third one is the data. The IoT and the server can share some data as the offline phase, which means as the initialization phase. It is like the secret key or secret information shared as a one-time password. Well, it's similar. And the third one is certificate or secret key. During the exchange, the data could be encrypted and another side could decrypt it to know the plain text. So in that case, that for an authentication, we can, let's say, we can combine password, Face ID, fingerprint, token, etc., etc. So here comes a question. If we use several authentication factors, is that secure enough to accomplish the authentication? The answer is no. Because that even we use several authentication factors, but we need to have a look how the protocol is designed. Here we need to mention the FIRDO Alliance, which is Fast Identity Online Alliance, which propose several user authentication specifications. The first one is FIRDO Universal Second Factor. We call it G2F. the U2F supports the second factor experiences. U2F allows online servers to augment the security of their existing password infrastructure by adding a strong second factor to the user login. The user logs in with the username and the password as before. The service can also promote the user to present a second factor device like a token at any time it chooses. And the second one is the further universal authentication framework. We call it as UAF. So UAF support a passwordless experiences. With UAF, the user carries a device with a further UAF stack installed. They can then register their device to the online service by selecting a local authentication mechanism, such as sweeping a finger, looking at the camera, speaking into the mic, enter a PIN, etc. The UAF protocol allows the service to select which mechanisms are presented to the user. Once registered, the user simplify repeat the local authentication actions whenever they need to authenticate to the server. The user no longer needs to enter their password when authenticating from the device. UAF also allows experiences that combine multi-factor authentications, mechanisms such as fingerprint plus PIN or plus password. And the last one, Client to Authenticator Protocol, CTAP. It is a specifications describing how an applications and operation system establish communications with a compliant authentication device over, let's say, USB, NFC, Bluetooth communication medium. And what about IoT? Here is a picture about the FDO. FDO stands for Fido Device on Board. It is a specification for automated, secure IoT provisioning technology. I will turn on my laser point. Here you can see on the first step, at the manufacturing stage of the IoT device, the FDO software client is installed on the device. A root of trust key is also created inside the device to uniquely identify it. The root of trust key can take the form of cryptographic keys built into the silicon processors at the time of manufacture, can be placed in the file system. Other FDO credentials are also placed inside the device together with the web address that will be needed later in the process. Last, digital proof of the ownership is created outside of the device. The self-protected digital document allows the owner of the device to identify themselves later in the onboarding process. Changing to the target cloud for the device can be registered by changing the ownership voucher without unboxing the device. And here is the second step. The IoT device passes its way through the supply chain. The ownership voucher follows a parallel path. And here is the third step. Once the target cloud is selected by the device owner, the ownership voucher is sent to that cloud or platform. In turn, the ownership voucher is registered with the rendezvous server, which is RV in the here. Let's back to the street. Rendezvous server, and the rendezvous server acts in comparable ways to a DNS server. And we now turn the first step. When the time for device onboarding comes, the device is connected to the network and powered on. After the device boots up, it calls the rendezvous server that was programmed into the step one. The device identifies itself to the rendezvous server, and in turn, the rendezvous server matches the device to its target cloud or the platform. The web address for the target cloud or platform is provided to the device. Multiple rendezvous servers can be programmed into the device, including both on-prem and cloud. Now we look at the fifth step. Based on the information provided by the rendezvous server in the previous stage, the device contacts the cloud or the platform. The device uses its root of trust to uniquely identify itself to the cloud or the platform, and in return, the cloud or the platform identifies itself as a device owner using the ownership voucher. Next, those mutual destinations allow a secured encrypted channel to be created between the device and the cloud or the platform. Now let's look at the last step, which is here. The cloud or the platform can now download over the encrypted kernel whatever credential or software agent are needed for corrected device operation and management. FDO allows the credential to vary so that IoT solution owners do not have to change their solutions when they adopt FDO. These steps complete the FDO process. The device contacts its manager platform, which will manage it for the rest of its life cycle. FDO last document, although it can be re-awakened or re-waked up in the event of a transfer of ownership of the device. Maybe it's too complicated. I will give you an easier example. Think about this case. When you hold your password and you want to cross a border, how the custom gonna check your password? It's easy. First, the custom gonna check your password if it is a real document. And then the custom gonna use the data on your password to verify if you are the real password holder. I will give you an example for the protocol. Here is the initial protocol. As I said that you have several, let's say, personal information on your password, some credential information on your password. So before give all the information to the readers, the password can check if the reader is the legal party. So here you can say, I can turn on my laser point. Here is the key of encryption, KE, and the password can share the KE to the reader. At this stage, that we assume that the KE is not possible to compromise by any adversary. In the real case, is that the password can put down the reader, and the reader can read some K through the OCR process. And then the reader can generate some fresh nouns, NR, and then encrypted the nouns with some information, let's say hello, with the encryption key and send back to the password. Here we can say that there is only the party, which means the only legal party who have the key of encryptions can decrypt the message. So in that case, the password can authenticate the reader. But is that secure enough? Well, the answer is no. Because if there is an adversary, that the adversary can replay this message, well, what happens? So each password can think, okay, the adversary is a legal reader. So the password can continue with further actions. So how can we improve that? Let's go to the protocol 2. Okay, you can say here the same, the password shares the key of encryption. And in this stage, the password also generates a nonce NT. And it first shares the nonce NT to the reader, and the reader can reply with the encrypted nonce NR and NT to the password. So, okay, this time, there's no more replay attack. But is that secure enough? No. we realize that there's no authentication on the reader, which means the reader cannot authenticate a password if the password is a real password or some, let's say, adversary or some hacker. So now we go to the protocol 3, how it works. Okay, as before, there's 2 nouns and the password shared nouns, and the reader reply with the encrypted nouns. At the final stage, the password gonna replay the nouns NR to the reader to show, okay, if I'm a password, I have the encryption key, I can decrypt your message to have the NR, and then I provide the NR to the reader to show, okay, I'm a legal party. Okay, it's cool. Now the password can authenticate the reader, and the reader can authenticate the password. But the thing is that, think about what we mentioned at the first stage. We do not only request the authentication, the mutual authentication, but also to change some informations. So the thing is that the NT and NR is known by the adversary. So if at the end of this stage, we use NT or NR or some combinations of NT and NR as the session key, well, all the information exchanged between password and reader can be known by the adversary. So how can we do? Now we need to mention the ideas of key exchange. Why need to mention that key exchange? Because the purpose of key exchange is to establish a secure channel between password and the reader, and all the information transmitted between IoT and the password and the reader through the secure channel is impossible still by the adversary. So here we can see, now we have the protocol 4. At the end of stage that we send the NR as an encrypted form. So which means that any adversary is not possible to get the knowledge about these nouns. So at the final stage that, okay, we can use NR as the session key to, let's say, for the purpose of the secure channel. Now I'm finished about the initialization, let's say, ideas. Here is a simplified version of the ICO 9303 back protocol. You can see here the password shared 2 keys. One key is for encryption and one key is for MAC. The MAC is as a signature. So firstly, the password and the reader generate a nouns, NT and NR, and also a key material, KT and KR. As before, the password gonna share its NT to reader, and the reader gonna encrypt it both NR, NT, and the key material generated by the reader, and then sign the whole message with key N. Once the password receives those informations, it's gonna firstly check if the message is modified by any third parties or by any adversaries. If yes, okay, the password gonna decrypt the message to have the NR, NT, and KR. Once it finishes those precise, it's gonna encrypt it NT, NR, and KT, which is generated by the password, and sign all the message to reader. At the final stage, they're gonna use KT XOR KR as the session key. So that's the simplified version of the PAC protocol for the password. So there comes several questions. Why we need both KT and KR? Because that, well, is that necessary? And second question is that, why cannot we use the key material instead of the nouns? Why we need them both? And the final question is that protocol secure? Well, I will leave those questions as a homework. You may find some interesting news during your search or research about vulnerabilities of French passport published several years ago. Okay, now let's go to the main topic of today of this session, Authenticated Key Exchange Protocol for IoT. Before that, what is an Internet of Things? You can see here in the photo that radar on the road, a temperature sensor, a cleaning robot, a camera, a car with GPS sensors with 5G connections, a rubbish bin with some detectors to check if the rubbish bin is full or not. They are all Internet of Things. So for them, what do we need to considering to design a protocol for them? I mean, a protocol of the authenticated key exchange. Well, it's easy. We need to consider the authentication, I mean, mutual authentication for both sides, and the session key establishment, which is the key exchange. But that's for the common scenario. What is the specific point we need to think about the IoT scenario? Here comes. For a common IoT device, they compare with a general device, they always has no same resource or has no same capacities. Well, as our phone, it can easily compute, let's say 10 power several large numbers. But for an IoT, even some encryption is hard for that. And the second point is that for some cost issue, that the manufacturer always want to decrease the cost for produce IoT device, which means that they cannot guarantee all security measures. And also, once the IoT device is deployed in some area, let's say some factory or even your home, the security update maybe not comes forever. And also the third point, as I mentioned before, there could be no human beings involved, which means that no human can type the password, no human can come to verify if everything works fine. Here you can say I have a picture to give you ideas how it works between an IoT and the server. On both sides, on the IoT and the server, they both have some public informations, and also they hold some private information. Let's say, for example, the secret key of the IoT device, and also another secret key of the server. At the beginning, they start with the authentication request for both sides, and then once the authentication is good for both sides, they can start the session key establishment. At the end of the protocol or at the end of communications, for this session, they will generate a session identifier and a session key. If everything goes fine, the session ID is matched on both sides, and the session key is also matched on the both sides. So what happened if an adversary just comes? The adversary can have all the public information of IoT and the server. And also the adversary can have all the information transmitted between the protocol, during the protocol. And there is some special adversary. They can also have the private information of IoT, maybe also the private information of the server. So in that case, when we design a protocol, we need to considering the several security properties. Here I list some, let's say, well-known or common security properties of authenticated key exchange. The session key security means that at the end of each session, the session key is not known by anyone but the participant. And the second one, the key randomness. In any successfully established session, the session key is uniformly distributed at random. And third one, key control. the session key cannot be assigned forcibly as any predeterminate value in any session. And next one, the key confirmation. In any successfully established session, a legitimate participant can confirm if any participant involved in the same session and holding the same session key. Next one, the forward secrecy and backward secrecy. It means that those properties ensure that the compromise of the long-term private key of some participant involved in a successfully established session does not compromise the session key negotiated in later rounds or in previous rounds. Okay, let's look at the known key resilience. It means that knowledge of a session key will not have a security impact on other session key. And the unknown key share resilience means that honest participant, let's say Alice, never ends up believing it shares a key with the other participant, let's say Bob. And although this is in fact the case that Bob misunderstands that the key is instead shared with another participant, let's say Charlie. It's a triangle relationship. And the next one, entity authentication. This property allows a participant who established some sessions to verify if indeed participants are actually involved in the same session. For the next one, well, let's assume the long-term private key of one participant is compromised. Well, for sure, an adversary is able to impersonate because the adversary knows all the private information of that device or of that party. However, with this property, the adversary is unable to impersonate any other no-compromised party to the one who is compromised. And the next one, server compromised impersonation resilience. In a server device setting, usually the server holds more confidential information. The property guarantees that even if an adversary has compromised the server, then it still cannot impersonate the server to any device. The last one, information leakage resilience. Assume that an adversary has access to some public and private information. However, this feature specific a bound on the data side. Thus, no unreasonable amount of information can be leaked to the adversary. Well, with those properties, how can we design an authenticated key exchange protocol for IoT? Okay, here I will show you a simplified version of Big Data Facilitated Two-Party Authenticated Key Exchange for IoT, which was published last year. At the initialization phase, which means offline, the server gonna first prepare some system parameters, and also it's gonna generate a big data site, which means that in this protocol, we're gonna use the big data as one of the authentication factor. And then the final step, the server gonna generate a tag for each data items with two secret key, K and K prime. At the final stage, that IoT device gonna has all the public parameters and the long-term key, master key MK, and the key prime, which is used to generate the tag. And on the server side, the server gonna publish gonna have all the public parameters, gonna have the secret keys like the long-term key, master key, a secret key SK, which is used to encrypt some information, and the capital key K, which is used to generate the tag, and also all the big data side and the tag. Okay, let's look at the protocol. So on the IoT device, first it's going to generate a Diffie-Hellman style ephemeral key. Before we continue to next step, what is Diffie-Hellman key exchange? Here is a short description of the defilement exchange. We have base value, we have the modular, we have the secret integer A, which is the ephemeral key of the defilement. And Alice can send the A, which is G power A, to Bob. And Bob also generates another ephemeral key B and send the B, which is G power B, to Alice. At the final stage, they can hold the capital K, which is the G power A and B as the session key. Okay, let's back to our main protocol. As the second step, the IoT device can choose some index of the data site. For example, that we already generate the big data site. Let's say we have 100 data items. Okay, the IoT device can choose randomly. I will use the first one, the third one, and the ninth, and the 100th. Okay, I will use those data items for further key exchange. And then the IoT device can hash all the credential values with MK, with the long-term key MK, and send those values to the server. Okay, the server, once it receives the information, it's gonna verify if the message is legal, is not modified by some third party or by some adversary. And it does the same thing. It will randomly choose some index of the big data site, which is different from the index set of the IoT device. And it can, based on those chosen choice, and it can generate a combinations of the data items and also another combinations of the text. And for sure, it can generate an ephemeral key of defilement. And at the final stage, it sends some hash values to the IoT side. The IoT side can, okay, for sure, verify the message and then verify if the combinations of the tag matches the combinations of data. If yes, okay, the IoT device can generate a final check-in message to the server, and also it can generate the session identifier and the session key. Okay, on the server side, the server can verify if the final check-in message is legal. If yes, okay, the server can generate the session identifier and the session key. Well, as I said, it's the simplified version. If you want to have the complete version, please find the full papers from the Google Scholar or some other source. Okay, let's say with 3 exchange, we achieved both mutual authentications on IoT and server. We achieved key exchange and the security properties such as perfect forward secrecy, key compromise impersonations, etc., etc. Well, is that okay for the property? It is a yes and a no, because today we still has a lot of challenges and new challenges coming day by day. The relevant topic has been researched for several years. However, there are still so many challenges and new challenges coming which to be studied. Here I list some examples. Firstly, it is a matter of subjective perception. I mean, to this day, there are still many people who believe that the security is not important and even feel that their data is worthless even if they lose it in time, until it is too late that their fund in their bank account has disappeared and important information or documents has been made public on the internet. Second, with the increasing number of different IoTs and the competitions between the manufacturing of different IoT companies, in order to keep the cost down, design and production are not always guaranteed, which means once let's say on the market, security updates are often not released even afterwards, or even not happened. And the third point, now we are slowly moving into the post-quantum era. the context between the efficient attack capacities or capabilities of quantum computers and the inefficient operation capacities of the IoT device means that the risk of a successful attack is much, much higher. And how to design a secure protocol and protect the industrial IoT infrastructures are always an open question. So thanks for your attention and feel free to contact me. And if you have any questions, feel free to ask and I would like to discuss with you. Thank you.
Thank you so much for that presentation. It was very interesting. So does anybody in the audience have any questions for Bowen?
Just one thing, well, if you want to have a full version of the protocol, the full version of the description of the security properties, or even the IoT standards for authentication of FIDO Alliance that I would like to share with you, please send me an email. Yeah.
Okay, great. Great. I guess people will be contacting you soon.
Yep. I will wait for the emails.
Absolutely. So is there any question left on the floor? Yes, we hear you.
Yeah, excuse me. It's again Kosigan. I just want to know, according to the Diffie-Hellman key exchange, you
Yep.
didn't mention the key size, the key size, and since we have a different kind of devices. You didn't precise the resource, because we can have just a microcontroller with a small store, a place. What can you manage it? I just want to know. Okay.
Yeah. For
you.
example, okay, it's okay. For this protocol, let's say I already reduced the computations or calculations on the IoT device, and I know that for the current version that there is still a high volume of computations or calculations because we have the development. And even we reduce the key length or the message space, there's still a high volume of the calculations. So if you find these papers, I have also a insurance version which reduce the calculations of the development on the IoT device side. So I use this version to just to simplify the descriptions or the presentations to give you an initial ideas. But with the improved version that for IoT device, let's say the much IoT device could handle this protocol. And also we are looking forward to find some other efficient ways to reduce the computations or calculations on the IoT side. So for some, let's say, microcontrollers, that we're gonna have a look about the capacities of the microcontrollers to, let's say, adapt our protocol to that device. Let's say. Yep. Thank you.
Okay. Thank you. Yes.
Our next presentation for today will be by Georgios Stamatis, if I'm not mistaken, and it'll be securing the infrastructure, detecting and mitigating threats. So I'll ask him to please share the screen. Okay, it's good. And well, Joseph, the floor is yours.
Thank you, Camilo, for the introduction. Good afternoon, everyone. We're going to see different aspects of C4IIoT framework. Some of them were presented in the morning earlier today by Serjan, but we're going to see them now from the aspect of the software and the hardware. So we're going to see a bit how this framework is securing the actual infrastructure, so making it less vulnerable to attacks. How the monitoring of the data produced by the edge is performed and how their integrity is protected. And then finally, we're going to see a case where a specific threat is detected and mitigated through the C4IIoT framework. So I'm going to go a bit over the hardware architecture again. We have the edge layer, which has the logistics devices. We currently have, I think, 20 such devices deployed and in use by CRF. And these Raspberry Pis are the edge for the smart factory. Now, the logistic devices, of course, since they're mobile, they send their data to the logistics field gateway, which is owned by the mobile operator, and from there to the cloud. The Raspberry Pis and the Smart Factory Field Gateway are in the same network, and they are also connected to the cloud. We also have our main cloud server, which has hosts most of our cloud components. And we have two additional ones. One is the trusted execution environment. It's an SGX enabled server where we run one module as part of this demonstrator. And we also have another cloud server which hosts modules which could not be hosted in the same server as most of the other modules. Now, from the side of software, on the logistics edge devices, which are devices with microcontroller-based devices, we have Baxi running, which performs analysis on these modules. Is software created in C programming language. On the logistics field gateway, we have the Decentralized Access Control, Medici, Data Fusion Bus, Traffic Analysis Module, and Bugs. On the Smart Factory edge, on the Raspberry Pis, we have part of Decentralized Access Control and another Bugs module running. On the field gateway, we have again Decentralized Access Control, Medici, Data Fusion Bus, Bugs, Disco, the Sdn Controller, and Traffic Analysis module. And finally, on the cloud, on the our main cloud infrastructure, we have Karmas, the Advanced Visualization Toolkit, the full version of Data Fusion Bus, BainSec, Security Assurance Module, the Cloud Bugs, and Decentralized Access Control System again. On the complementary server, we have our private Docker repository and the private certificate authority, some components of Decentralized Access Control module. And on the SGX-enabled server, we have one version of Bugs for the logistics use case only, running on this server only. What I wanted to add in comparison on what you saw in the morning between the different layers and levels, here this is representation based on the layers mostly, meaning the edge, the field gateway, and the cloud. And the levels, since there are components which exist in more than one level, such as the Decentralized Access Control and the Data Fusion Bus, so that's why they're repeated many times here in this slide. So let's start with the logistics edge. This logistic board was specifically designed for C4IIoT by the University of Novi Sad. As we already mentioned, the data are transmitted through a mobile network, a A1 Serbia network, which is, of course, mobile networks are secure by design, and the data transmitted directly to the mobile operator server, which is the logistics field gateway in this specific case. This logistics device is equipped with Infineon's Optica Trust M chip, which adds to the security. And the BACS model, the machine learning model running on this device, which of course cannot support high-level languages, is developed in C programming language. And the data it collects is mostly the GPS location and the acceleration of the board itself. And these are transmitted to the field gateway. The smart factory edge is about data. The actual edge here is the automated guided vehicles as described by Serjan in the morning. The data from these devices is transferred to Raspberry Pis, which again are enhanced by Infineon with Optica Trust M and Optica TPM2. Here we have Python BACS model running and evaluating the data produced there. And in order for this model to run, a Docker image which can support the ARM architecture, which is the architecture of Raspberry Pis, was created. The data in this case is the velocity and the speed and about the two motors of the automated guided vehicles. So we're moving on to the logistics and the smart factory field gateway. These are two completely different servers, but they have many common things. They're both isolated from the internet, and they are connected to the cloud through a secure IPsec connection. The logistics one is a Linux machine, where the smart factory is a Windows machine. This part shows us that the C4IoT framework can work with both operating systems and add to the security of both of these. And I would also like to mention Medici here, which is part of the monitoring process, but it's an offloading mechanism module, because it constantly monitors both the field gateways and the cloud in order to choose where the evaluation should take place of the data that produced at the edge. So in case of an attack or of another reason why one of the servers might be overloaded, this module would send this data for evaluation to another one, which will not be so heavily used at the time. Moving on to the cloud, most of the modules are in the main cloud server, as it was mentioned before, secured behind a cloud infrastructure, and only the services that need to be accessed from the field gateways are exposed there. We also have the SDX enabled environment, which I mentioned earlier. Now, this main infrastructure is using MicroK8, which is a lightweight Kubernetes version, and most modules are running within it, and it is protected with an ingress point, which does not allow access to modules which do not have the required certificates. I'm sorry, excuse me. This is from the dashboard of this Kubernetes version. On this screen, we can see the load, the workload status to the operator, to the security officer of the organization the C4IoT protects. This could be useful because it would show easily which services are running and which are not. And if some of these are having trouble, which could be an indication, let me say, not proof or anything of an attack. And there is more information about the pods running within the Kubernetes cluster here. This is the total CPU usage from all the pods and the memory usage. Spikes in this could also be an indication that something is not working as expected and maybe should be investigated. Below is the list of the pods. And by selecting a specific pod, the user can see more details about this one, such as the specific CPU usage of this pod only and the memory usage, and some more information about when it was created, how long it has been up, and things which could potentially be even useful for forensics if required. But it keeps track of all the services that are running on the cloud. Moving on, the next modules add to the security of the overall system. So I have not assigned them to a specific layer of the architecture. Within C4IoT, we are using private certificate authority as the main way to implement the identity management of this project. This private certificate authority has this user interface. This is a screenshot with a list of the certificates that have been produced on it. But of course, there are other functionalities. You can create the certificates on it or just sign them using this certificate authority. And you can also revoke certificates in case you think one of these has been compromised or for any other reason that you don't want it to be valid anymore. Now, this certificate authority is of course used for all C4IIoT modules. It's heavily used by Kafka and Data Fusion Bus and the Decentralized Access Control module, and in all SSL communications. Now, as part of this identity management, of course, each module has its own certificate, and the user, let's say, of this module is identified by this certificate. Another module deployed on the cloud is the security assurance module. Now this module has a list of the organization assets within it with as much detail as possible. The user can update them, of course, and can perform vulnerability analysis on these assets that has information about. On the bottom here, we can see a specific vulnerability detected, for example, which of course has the CVE for this vulnerability and impact and a base score depending on how serious this vulnerability is. So security assurance module can also perform dynamic testing, which can reveal other vulnerabilities. And part of it is also Everest, which using event captors can monitor specific services and if they're running okay. So in case one of the services stops running or something not going well is detected, this will be reported by this module. On this screen here, we also have some overall information about the assets and how many of them are active right now. And by vendor, we're talking here about the vendors of the software, how the software is separated by vendor, and activities by type. I'm sorry, this screenshot is too small. Yeah. And additionally, almost every module for this framework is Dockerized, so it has its own image or it is using a ready image from Docker Hub. So a private Docker repository, Harbor installation, has been used here in order to store these Docker images and use them and pull them directly for this repository and not from Docker Hub. Now, this gives an advantage in case the external repository is somehow compromised. You know that you're always using specific images. These images are tagged with specific tags, so we'd never call the latest from an external repository. And of course, the custom images are also stored here, the ones that have been created using Docker files for the special needs of each component. One of the most important aspects of this Docker repository is that it performs vulnerability analysis on the images stored here. So as you can see here in this, this is a specific image called the S-connector, and 3 different tags of it. So the first one had 291 vulnerabilities, the highest of which was critical. And after the first patching, it dropped down to 75 ones. And then we decided to use a new image which had 0 vulnerabilities, at least when we imported it. For each of these images, each of these artifacts stored on Harbor, you can see the specific vulnerabilities, a list of specific vulnerabilities detected with the severity, and also if there is a fix, and if there is a fix, which version of this specific software fixes this vulnerability, and of course the package that this vulnerability was detected. Now I'm going to move on to BinSec. BinSec is a binary analysis module. It can be used to perform analysis on binaries. Now, this interface that you're seeing here is from the Advanced Visualization Toolkit, which is developed by Aegis. BinSec is developed by CEA. Let me start the video. Okay. What the user can do here is perform the binary analysis on the binaries of BugC, which is the bugs developed in C programming language mentioned earlier. You can choose the method, which version of bugs to analyze, and the input. We have 3 different types of input which will be used during this analysis. Now this is a result. This analysis takes time. It can maybe be given 5 minutes or more. So we're going to, what we saw there was an analysis that was performed earlier. And these results can be used to check if this binary is working as expected. Now a few words about the Decentralized Access Control module, which is developed by IBM. It has 2 very important aspects of our framework. One is that it offers an API for encryption, attribute-based encryption to be more specific, which is used by both use cases. And then it takes 2 different approaches on the blockchain element. On the logistics use case, the blockchain's database is used, which is a database with blockchain characteristics. So again, the immutability, for example, is its main characteristic. And for the smart factory, we have a blockchain which is using hyperledger fabric. In this figure here, we can see the flow a bit for the logistics use case, but we will see it more in details later on. This is another module which exists on both the field gateways and the cloud is the Data Fusion bus developed by ATML. Its main component is Kafka, and its main use is to help with transferring of data between the rest of the components. And I mean, most of the components are using it to send data and exchange data between them, but not all. Of course, we have also REST APIs. Kafka is here because it can support a very high throughput of data, much higher of what we have right now. It offers some, at some point, resilience to the system. And of course, we have different topics depending on the needs of each module. The topics on Kafka equivalent to queues on message brokers. Now, the extra part that we have here is the Data Fusion Bus Admin API, which exposes a REST API to be used by the AVT. And the user through it can give read and write access restriction per topic per user. The user here is again identified by the certificate, so the common name on the certificate, and also revoke the access that has been given previously on some of these users. So, for example, for the cloud installation of DFB here, the user, there is some information received by this REST API about the health of the broker and the topics, and the user can also ban previous access of a specific CN using this functionality here, and can also add a new user using this functionality by giving it access to specific topics. Now the storage connector is running only on the cloud installation and the Elasticsearch. Its main functionality is to store data from a specific topic and take the data, consume the data from a specific topic and store them on Elasticsearch. But it is also be part of the data integrity system by performing checks on data using the decentralized access control module mentioned earlier. So we're going to move on to the monitoring, specifically of the logistics use case. The data, of course, are produced on the edge device, as we mentioned earlier, the data about GPS, acceleration, and there on this device, on this microcontroller's device, the first evaluation of this data is performed using the BACC module. And then the data are sent to the mobile operators, to the logistics field gateway server over the mobile network, of course. And they are received by a program there, which its main job is to receive this data and prepare them for the next step. Now, one of the checks that is performed here is actually, let me start from one of how the decentralized access control is used here. Now, the data, when they are received here, the hash is added to the blockchain element here, the blockchain database more specifically, and the data are encrypted. Both these functionalities are supported using the decentralized access control module, of course. And then, depending on the confidence of the evaluation on the edge of the confidence of the model that evaluated this data on the edge, they will either be sent to Medici or directly to the cloud through Kafka. Now, if the confidence is low, they are sent to Medici because in this case, we want to reevaluate this data to see if we can achieve a higher confidence on the results. The evaluation we're talking here is anomaly detection, as it was mentioned by Serge in the morning. So the data are evaluated to either be okay or as anomalous. So the Medici, which is a module developed by the University of Greenwich, will receive this data if they have low confidence, and then based on the information it is gathering from the field gateway machine and the cloud machine, will choose whether it will send this data for reevaluation to the BACC module running on the logistics field gateway or to the BACC module running on the cloud field gateway. Of course, both these modules, in order to use this data and reevaluate them, they will have to use decentralized access control on their respective layers to decrypt the data and then reevaluate them. Once this reevaluation, if required, is complete, these data are sent to a specific Kafka topic where they are consumed by these two modules. One is the storage connector, and the other one is the advanced visualization toolkit. Now, the storage connector in this particular case, apart from attempting to store the data, actually before storing the data, it will decrypt them and attempt to match the hash after rehashing the data to match it with the one stored on the blockchain element at the field gateway layer for this use case. Now, if this if these two hashes match, we have high certainty that the data were not tampered during while they were in transit from the field gateway to the cloud layer. So, and we'll store them on Elasticsearch on our storage here. If the data have been tampered, it will again store them on Elasticsearch, but it will use a different index which only contains data which we consider that they have been manipulated, and they are stored there in order to be analyzed by a security expert later if needed. The Advanced Visualization Toolkit also consumes the data live from Kafka in order to display them to the user. And of course, it also has access to the storage in order to display historical data when required. Again, the Advanced Visualization Toolkit will have to use the Decentralized Access Control module in order to decrypt the data, and it can also use it to perform a hash check on the data that it has received, either for the historical analysis mostly. So this is a way to check the data integrity for the data that at rest that have already been stored. Now moving on with a video from the Advanced Visualization Toolkit, we're going to see some of the screens for the logistics use case. Now the event screen receives all the data from the logistics use case. On this part of the screen, you can see where the final evaluation took place or while analyzing the data, if it was at the edge of the field gateway or the cloud. And the specific data points here, if you click on one of these, you will see more specific information about it. So moving on to a more specific screens, which here we can see data about specific devices. When you first visit this screen, of course, you have data about all the devices again, and this graph shows the ratio of OK versus anomalous events. And these here are the last entries received. And then you can select a specific device. These are actual devices deployed right now. And see the data, the last data received about this specific device. Here it's using both Kafka and the latest stored data points. If there was an anomaly, the last detected anomaly would be presented here. Here you have the actual sensor data. They have been decrypted. And since we're talking about the GPS data, we have a visualization on the map as well. Now, moving on with the historical analysis of the data. There are two different screens again here. One is used to see the data here by selecting a specific device and the date, a specific day. Let me just point out that on this screen, since we're talking about historical data, you can also validate the integrity again, calling this specific data point where you can see its point on the map again, and clicking validate integrity, the hash of that is stored on the blockchain and the hash of this specific data point received from the database are matched, so the integrity is verified. Now on this screen, we have a timeline analysis where the data are presented on a timeline. So you know when these specific data points were received. during the time of the day. And this graph here shows the final detection layer, if it was the edge or the field gateway. And this also shows if they were okay or anomalous events. And of course, the integrity of this specific data can also be verified again with a hash check. Now, as part of the identity management, while the user of the system can view the data on the advanced visualization toolkit, we cannot verify that they own the data. So in order to actually download the data, you have to use your own certificates. In this case, these certificates are used to get new encryption keys from the decentralized access control module if you have the appropriate role. And these new encryption keys are used to decrypt the data again, and then you can receive them in a CSV format, as we will see in a few seconds. So if I don't have the required certificates, in this case, I cannot download the data because we cannot verify that this user that is trying to download them actually has the permission to do this. So we're going to see the CSV with the data right now. As you can see, we have information. The device ID is a unique ID for each device. We have information about the detection, if it was a key or an anomaly. If there were any anomalous detections, here it will mark as an anomaly, the timestamp, of course. And these are the actual data, the acceleration, and the GPS information. And these are the data of a whole day here. Now moving on to the smart factory monitoring. The flow here is almost the same. Again, but in this case, the edge, of course, is not mobile devices. They are the automated guided vehicles which send their data on the Raspberry Pis. There, the data are again evaluated by the BACS module. And but in this case, the data has added to the blockchain element of the decentralized access control on the edge, on the actual edge. And of course, the data are encrypted here before they are sent to the next layer. Again, if the confidence at the edge is low, the data will be sent to Medici. If it's high, they will be sent directly to the cloud. When I say directly here, it's not that this layer is bypassed, since this module cannot directly access Kafka here. There is a second installation of Kafka on this layer, but for simplicity in this figure, we have omitted this. Again, Medici will have to decide whether the re-evaluation of data will take place on the field gateway or on the cloud layer, and send the data to the respective BACS modules through Kafka again. And of course, this module will also have to decrypt the data before attempting to re-evaluate them, and the result is again sent to the cloud, where again it is consumed by the storage connector and the advanced visualization toolkit. The concept here is exactly the same as the one that was mentioned before. The data hash is checked against the one that was stored when the data were produced at the edge on the blockchain element. And after the data are stored on storage by the storage connector, if the integrity checks out, if the hash comparison checks out, And after they are stored, also the primary key, let's say, of Elasticsearch that is received after performing the actual call that stores the information is also added to the blockchain. Let me add here that each entry to the blockchain element is accompanied by the unique data point ID. So each data point created at the edge has a unique ID, which is a combination of the device ID and the timestamp at this time. So we have unique IDs, and these are the unique identifiers of each data point. And this is how the data, each data point is uniquely identified. And I would also like to say, to mention here about the decentralized access control, that when the data are encrypted, a policy is also added to this encryption. This policy determines who can actually decrypt the data. So it could be either a user in an organization, a type of user in an organization, or a domain, because the bugs algorithm models running here will also have to decrypt. But someone who doesn't have this role or domain or organization in the certificate will not be able to decrypt this data. And again, the advanced visualization toolkit here also consumes the data both live from Kafka and can also retrieve them from storage for historical analysis. And of course, the integrity of the data at rest can again be verified using the advanced visualization toolkit. These are some screenshots from the AVT. This is a screen similar to the one we saw before for the logistics use case, but in this case is for the smart factory use case. Again, we're interested to see if the final evaluation took place on the edge or the field gateway or the cloud. The data points are received here live from Kafka, and if you click on a specific one, you can see more information about it. Here, the data are not decrypted, so you only see the information that is outside decryption. We're not only the sensor data are actually decrypted, the data that are used to evaluate each data point. And again, we have the confidence and where the final detection took place. And a graph that shows the ratio between OK and anomalous events. Now here we have selected a specific edge device, HGV2, and we can see the data in this case are actually descripted so that the user can see them here. Then they're displayed to the graph. If there was an anomaly, the last detected anomaly would be displayed here. And again, a graph that shows the ratio between OK and anomalous events. And this is a screen from the historical analysis of the AVT. This is actually from our previous prototype. Here, the user can also perform validate the integrity of the data received, and the acceleration and the velocity of the motors can be displayed here. As we said earlier, there are two motors on each HDV device. On our latest version, these two motors are monitored separately and not as one device. Now a few words about the traffic analysis module, which is the main module that can attempt specific detections, specific attacks. This, in this case, is some types of malware, some types of man-in-the-middle attack and session hijacking, some brute force attacks, and some network scan attacks. This module runs on both field gateways and is monitoring specific network interfaces there. And the Sdn Controller, DISCO, is so the Sdn is a software-defined network, only exists in the smart factory, and can be controlled by this module by attempting to ban an address or a MAC address or an IP1, in which case this host is isolated from the rest of the network, or block a specific port to a specific IP only, or limit the throughput of the data allowed to be sent there. Now we're going to see the role of these two modules in the detection and mitigation flow. Now we are assuming an attacker, it could be an external, it could be a device that has already been compromised, is attempting an attack through the network on another asset of the factory. This attack is detected by the traffic analysis module, and it is reported through Kafka to the cloud. Now, this attack is received and displayed directly by the Advanced Visualization Toolkit, but it is also received by the Security Assurance module, which, as we mentioned earlier, contains a list of the assets, so it will use this information about the specific assets and extra information to enhance the message that was produced by the traffic analysis module, and then send it again to the AVT. Now, the user of the AVT will request mitigation actions from Karmas. Karmas is a module that suggests mitigation actions depending on the threat that is detected, but I'm sure Camilo will elaborate on this on the next presentation. And then the user can, through the AVT, can apply the mitigation action suggested by Karmas and block the attack. Now we're going to see a demonstration from our test servers. This is from the previous prototype of C4IIoT. What we're going to do here on this console, we're going to start a brute force attack between two actually there are Docker containers in this test system, but it is assumed that there are two different assets of the factory. So this attack, which takes a few seconds to start, is using a list of passwords, so it's a dictionary attack, and attempts to find through brute force the username and password of the SSH username and password for the other asset. What we're expecting to see here is that this report will start being reported by the traffic analysis module once it has been detected. It takes a few moments, but as you can see, it has already begun to be reported by this module. And we also have a flashing warning here for the user that a specific threat is detected. Again, of course, if we click on a specific the point here, we will get more information about it, that the device that was detected was a traffic analysis module on the field gateway of the factory, and that we do not get a specific attack at this point, but we will see it at the other screen after pressing on the threat detected flashing button, which will take us to the attack monitoring screen. Now on this screen, the user has more information about the attack. Here is a list, which of course are right now are these attacks which are detected continuously, since this is a continuous attack. And here we have more information about the specific attack, the source IP, the destination IP, and the type of attack were detected by the traffic analysis module. Now the rest of the information is added by the security assurance module. Now here we say impact and risk, but these have been replaced in the later version of this framework. And the security assurance module has added some more specific information here, and the user can also read more details about the attack in this window here. On below, like I mentioned already, the user can see the list of the attacks, when they were started, what type they were, if they have been mitigated, And by clicking in each one of them, we'll get the specific options that are above here. Now, the options that the user has here is either to ignore the threat or request a mitigation plan, which is what we're going to do now. As we mentioned already, this action will send information about this attack to Karmas and receive a mitigation plan from it. In this case, it's going to be a host isolation, which means block this IP so that it doesn't have any access to the network. And what we expect to happen now by clicking on apply the mitigation, this action will be applied by Disco, the Sdn controller that we mentioned earlier. And as you can see, the attack which was running up until now has stopped. What we're going to also do now is stop this attack and try to restart it just to verify that this host is actually isolated. And as you can see at this point, the attack does not even start, because this specific IP can no longer be reached. And moving on, close to the end, we have also an automatic mitigation mechanism here, where the user can set up specific mitigation rules, probably for assets that they consider most important. So they want them monitoring, and if attacked, to defend against this attack as soon as possible. So the user can set up a specific IP address and a specific attack type from the ones that can be detected, and a specific mitigation action, and create a rule like this, in which case this rule, the flow is similar, but in this case, again, the attack is detected by the traffic analysis and is reported to the cloud. But the connector, every time it receives an attack like this, it checks if there is a rule set up for this specific attack, for this specific IP and specific attack action. And if there is a rule for it, it will automatically apply this rule using, again, the Sdn controller. This concludes this presentation. Thank you for listening, and if you have any questions, please.
Very well. So today's final presentation is called the Automated Mitigation Search, a Constraint Object-Oriented Logic Programming Approach. And it will be given by me, Camilo Corra, from Université Paris 1 Panthéon-Sorbonne. And as Jurgis mentioned in his previous presentation, I will go in depth a little bit more into one of the modules and components of the C4IoT framework. So first, let's go over the outline of what we're going to see today. I'll do a brief introduction to the topic. Then we'll go over the constraint object-oriented logic programming approach. This will be the first part of the presentation, and we'll try to cover in detail what it is and why it is interesting and useful for this type of problem. Then I will dive into the details of the tool itself and how it works, and some other related work that has been done in the area. And finally, we'll cover and conclude with the presentation with some big high-level overview of what has been done and what's left to be done. So if we begin, let's think about the motivation of why this is an important problem. And let's restate what the
Camilo, I'm sorry for interrupting you.
Yeah.
I think that the screen is frozen for me, at least. I don't know about this. Yeah.
It's frozen.
And you're not in presentation mode, are you?
I should be, yes.
I see the The PowerPoint screen, not the presentation mode.
Okay, hold on. Is it better?
Yes, now we're seeing presentation mode.
Okay, thank you. Thank you for letting me know. I'm very sorry. So where was I? Yeah, so I was trying to go into the motivation of why we should study and why this is an interesting problem. So essentially, breakthrough attacks that go through the preventive measures cannot be solved with purely preventive solutions. So something must be done at runtime to tackle this problem. And ultimately, as is seen in the C4IoT project, it's the human operator who ultimately must take the final decisions. So frameworks like C4IoT must focus on helping these operators make the right choices when it matters. But this is a very complex decision problem, and whatever you decide to do will probably have strong impacts on the underlying infrastructure. So what is the problem concretely? If you're giving some information about an attack, what are the best actions among those that you have that you can do to mitigate it? How do you respond to an attack that's going on at the moment? So our take is that we will propose a tool that can interpret the set of suspected attack actions, can find solutions and mitigations to them, and then presents the solution who can execute or change them, as we saw in the demo a minute before. And we believe that with an extension to logic programming, this can be tackled in an efficient and modular fashion. So let's talk about logic programming, because if we're going to talk about constraint object-oriented logic programming, as in the title of the presentation, we got to cover logic programming. So here I'm going to try to give you the bite-sized, most condensed introduction to logic programming that hopefully has enough detail to be clear about what it is. So in one simple sentence, and this is all you need to take away from this part of the presentation, is that logic programming is the idea that a subset of first-order logic can be used as a Turing-complete programming language. So it can be used as a general-purpose language like Python or the others. It unifies knowledge representation and execution of a program as a single thing, as a single process through automated inference. Everything is proving theorems from the knowledge you state. It's declarative in nature, so it's different from what most of us are used to, because it focuses on stating only the problem's what and not the how in general. So you can focus more on the high level ideas and less about how exactly your code must be executed. And it has very strong theoretical underpinnings and more than 50 years of research and many implementations, both commercial, open source, available. So diving in deeper into logic programming, you have Prolog. So Prolog is the original logic programming standard. It's basically the standard in the community. It's invented in the 1970s as a result of the work of several researchers, especially in natural language processing. And it then became an ISO standard a couple of decades later and has since proliferated with many projects using it, especially in the commercial side. And essentially what you do is, as I said, is you describe everything as a set of mathematical relations, and then you execute queries as if it were a database, but it's a lot more than just a database, because it's not only knowledge representation, but also general purpose programs. And what you get as an answer to these queries is essentially a truth value. So if it's true or false, what you're asking, and then the values that make it true. So that's how you get useful information out of it. Very briefly, every Prolog rule essentially has this form. There's only one single construct in the language, which makes it extremely simple. But because it is simple, it is powerful. So in particular, head colon dash body, what it means is think of it like an arrow, and it can be interpreted as logical implication. So it means that the head, what's on the left, is true if the body is true. So a body is basically, just think of a conjunction of terms. Imagine first order terms, so you know, a function symbol and the arguments inside, and you must you must have a series, one or more of these in the body. And what they mean is that it essentially you're giving the meaning to how, under which conditions a given rule, a given relation holds. And if you simply state the relation, it means that it holds unconditionally. And we'll see some examples in a minute. So the way Prolog works is super simple, and we can see it through this example. Imagine this simple rule. It says P is true if Q and R are true. So think of propositional logic, the simplest of the simplest kind. So what Prolog sees is that it means that if I want to see that P is true, I got to first go and find what if Q and R are true. And so if this was our program, P if Q and R, Q if S, and then it holds that S and R. Then if we thought about what the corresponding logical formulas would be, you could see that if they form this conclusion, you can deduce P. Why can you deduce P? Because, well, Q is implied by S, and S holds, and we also see that R holds, therefore Q and R hold, and therefore P holds. Essentially, it's doing a very similar process to constructing a proof of the statement that we're asking it about. And essentially, it does what I just mentioned. So understanding how this executes and how it works is really a matter of thinking that it executes things in order and then dives down depth first and then goes back up and continues proving down the tree. And I'll do a simple example so we can close off Prolog, because Prolog, even though it's intimidating, it's a very simple language. So think of the following graph, very simple, directed graph we all know. So let's think about how we represent this. Well, it's very simple. We just simply list the edges as we would, well, perhaps we wouldn't do this in the same way, but here we're still stating a relation. We're saying an edge is a relation between two things, and we state between which things it holds. And then those are the facts. So we want to know things, especially if it's a graph, we might want to know paths through the graph. So here's the rule. We say that a node is always connected to itself, so I can always reach myself if I took 0 steps. And then there's you could say that a node is connected if there's an edge between two nodes. And this essentially is the way you express the transitive closure of the edge relation. So in an extremely small amount of code, we already constructed a very complex mathematical object here. And so what can we do with this? Well, how do we talk to it? How do we talk to our code? So essentially, first we can ask simply, is there anything connected to anything else? And it immediately tells us the answers. So notice with the semicolon, I am asking for the other answers, because since I showed before, Prolog not only gives you one answer, but if there are multiple possible answers, it gives you all. And note this first one, it's saying that this is true if essentially the solution is that they both must be true. And we know this because by definition, the nodes always are connected to themselves. So here it's proving this equivalence for us between these two variables if they were unbound. It's the most general information I can extract from the relation I have. Otherwise, it'll give me the specific paths. You see, it will tell me X can go to A, can go to B. It can tell me A can go to D through B. And then it goes on and tells me that A can also go to E through D as well. But then notice that there are many other solutions because there are other paths that can be taken. And at the end, it tells me false. That doesn't mean it failed. It means that it looked for every single other solution and it exhaustively examined the entire search space, and then it gave us a solution. So this means that Prolog has a complete execution strategy if the recursion depth is finite. And as I mentioned, this first response was special because it's the type of thing it's almost meta programming in some sense. Can we do more than this with only the code we have there? Well, we can test a specific query, and it'll succeed because first it'll go and check and it'll say true, but then it'll also say false, and it'll say false because it'll also exhaustively check that there are no other ways that connected A to B can hold. And this is because our relation is inherently non-deterministic because we have two different definitions. We have one which is only a fact and the other is a rule, but we need it so it can be recursive and have a base case that it can break the recursion. And we can traverse the graph in the forward direction, as I showed in the previously. So you see A to what, and it'll tell me, well, A can go to itself and all the others through the B line, but it can also go through the other way. So here I asked for another solution and it backtracked. It went back and through the choices that it made when it was proving this goal and says, in fact, there's other ways to prove. And that is why it essentially repeats some of the solutions because it's traversing our graph again through another path. And if you had a meta mechanism to understand this, then you could, either create a set if you only want the nodes themselves and so on. And this is the two special things in this answer. But we can do even more. We can actually run checks to see that if something isn't the case. And then we can do the graph in reverse. So it's not simple functions as in most programming languages. These are true mathematical relations, and I can execute them in any direction I want. So I'm going back. I already know my destination, but I want to go see what would lead me there, and so on. And in this case, it is also because of the multiple recursions. I'm sorry, the multiple paths back to A that it'll report it again. But this is because of the inherent structure of the graph. It's a feature, and this is the complete solution if you had an exhaustive search on this. So, and as a final extra bonus to Prolog is that there's a logical rendering of our program. We can transform our code into the corresponding logical equation that represents exactly what it means and that you can use to prove properties about your program. The asterisk here is because I am omitting intentionally some technical details as to how this is achieved and some additional things that must accompany the formula. But in principle, this is what you can do with logic programming, just as you can in principle do it with functional programming, that you can construct the mathematical model that is besides your code. So now that we're here and we've covered what logic programming is, I'm going to cover the extensions that we need so that we can get to constraint object-oriented logic programming as a paradigm. So constraint logic programming is logic programming, but you can use constraint programming. Constraint programming is a programming technique where you specify constraint satisfaction problems. And these problems are very simple. They are this structure, which is essentially three things. There is a domain or a set of domains. There are some variables, and then finally a set of constraints, a set of relations or equations or other related concepts that relate the variables to each other and that must be satisfied by any assignment to the variables. So what you're looking for is an assignment to the variables that makes it your equation or whatever you're using true. And we'll see a very simple example. Imagine that I told you that the domain was 0 to 9, so the numbers 0 to 9, and that the variables are these letters here that I'm showing you, send more e. Well, imagine I gave you this constraint. If I built numbers with my individual number variables there, so send in the 10,000th place, e in the 1,000th place, and so on, can I find a solution that makes this equation true? Send more money. And indeed, there's a solution. If you look for it and if you try this, you will see that this is the solution. This is a correct assignment of the numbers that makes this true. So as it turns out, constraint programming is a super powerful formalism that works very well for solving combinatorial problems, because essentially you're drawing elements from domains until you find the combination that fits. But very many other computational tasks that we're used to can also be done in or framed as constraint problems. For example, SAT solving is also can be seen as constraint programming, or can be formulated as a constraint problem. Real and rational equation systems, bounded integer equation systems, which is specifically the one we use in our tool, and even Prolog itself in a meta level can be seen as a constraint solver over these what are called Herbrand terms, which are essentially the first order terms I was talking about a little earlier. So let's look at a very simple example. So let's think about the example I gave you a couple moments ago. And here is our translation into Prolog, into code. And as you can see, essentially we're saying that the puzzle here on the left holds for some variables if, well, the variables are a list of this form, that they all belong to this domain, that they're all different, which is this, one little extra constraint which I forgot to mention. And then you pose simply the equation, just like I told you, and you give it the equation itself, and well, do we get to the behavior we want? Well, yes, we can even ask for what are the logical consequences of this mathematical relationship I gave you, and it'll immediately deduce that 9 must be S, even though it doesn't yet know the others. It knows that whatever the solution is, it necessarily has to have these values already bound in this way. And you can, in principle, replace all the code that is here by this code that is generated, because it is the logical consequence. And you see here that it has restricted the numerical domains of all the variables as well, guiding you towards the solution. So, and then can we get the exact answers? Of course, we can ask which specific answer makes this true, and it's the one I gave you before. But if you can also ask, are there more? And it'll exhaustively prove that this is the only solution that works. But if there were more, you would get another solution until it can no longer find any. So this is a constraint logic program. So now it is time to turn to object-oriented logic programming, which is one of the final aspects we need to form this program paradigm. So what is it? It's another orthogonal extension to logic programming, whose idea is to make Prolog more modern, more composable, and so you have programs that are no longer in isolation, but they can be composed with each other, and that you can form hierarchies, so you can reuse already code that is already done, and you get close to the modern software engineering practices that are common in Python and Java and so on. So there are several possible approaches to this specific paradigm, but we'll choose a specific language because it is the best documented and maintained. And there's one thing that I must mention is that objects do not have a state in principle, because here it's about relations and programs of the sort that we saw before. Those are the objects. It's not what we're used to, and where we have accessor methods and we modify the internal state of some data structure. So what is LogTalk? LogTalk is a object-oriented extension of Prolog, which has additions for functional programming, event-driven, and parallel programming, and it is generally aiming to replace the use of the module systems for the old Prologs, but also giving a lot more structure to your applications. And it's inherently compatible with the previous paradigm of constraint programming because it is orthogonal. And it is orthogonal because it is a transpiler. It works similar to the way TypeScript works with JavaScript. So it's a language on top of the original language, but creates only pure code in the original Prolog. And uses Prolog first order terms. It allows us to use them for a lot more, and we'll see that in a minute. And it has a rich reflective type system that can allow us to analyze and create complex hierarchies, just as we can do to represent taxonomic knowledge. So essentially, it retains everything that I showed you before in Prolog. Just there's a tiny bit of syntax on top for it to work. Essentially, they are extensions and of the primary extension are the objects, and essentially what they are is imagine the code we showed before where we observed the graph. You could in principle have a code in general for any graph and give the information through one of the arguments of the graph, and through that instantiation you have the particular graph. But we'll see this in detail with an example. The key selling point here is that you can create very complex type hierarchies, and this is important for what we're going to see next when we come to the implementation itself. So here I mentioned, imagine a rectangle. This is a first order term with two variables. So you have a rectangle, this is your function symbol, and then you have two arguments, width and height. So let's think about this. How do we represent this in Prolog? Well, in LogTalk, what you can do is you create this object, which has these two properties, and you can define predicates which hold for this particular theory. So imagine we were writing a mathematical theory of geometry. This is some of the things we would have inside. So what is the definition of area and perimeter and so on? But it doesn't represent a specific instance, because since we can give it the specific width and height that we want, and since Prolog allows execution in any direction and so on, it's much more powerful as a mechanism. Then how do we query it? Well, it works exactly the same way as Prolog does. The only difference is that now we really are talking about, so for this specific object, does this relation hold? And this allows us to do polymorphism and all these other important tasks in engineering our applications. And we can do the simple checks as we did before. So we can actually do extensions of this code as we would in object-oriented languages. Here we're going to declare a subtype, a square as a subtype of a rectangle, and we're going to simply, through unification, you'll see that it says the single side of the square is actually both sides of the rectangle, and through this mechanism, it can now use everything defined for the rectangle. And then we can reuse the code for the ancestor object without having to redefine it, which is something that was missing in logic programming until object-oriented logic programming came around. So when we put these two things together, we can actually do more interesting questions. So imagine as a question, do squares with side 3 have the same area as rectangles with 3 width and 27 height? Well, if you look at it, in fact, the answer is yes. And the fact that this goal succeeds and the unification is correct means that with Prolog we have proven this property. So the final little aspect before I finish this first part of the presentation is that essentially you can add all these other services to logic programming to render it a general purpose language that works for most problems, and not just these search and combinatorials. They can interact with any language through REST APIs, and it has good mechanisms to allow easy in and out. And here is a very simple example of a hello world in Prolog. Everything that's above this line is simply initialization code, and this is all you need to display a hello world web page. So in summary, why do we want constrained object-oriented logic programming? Because logic programming gives us very powerful AI formalism. Constrained programming gives us very efficient solvers for many mathematical domains. Object-oriented programming makes logic programming modern and allows us to represent complex taxonomies of objects. It has code reuse and it scales well to large models, and it has good tools for modern software engineering. And service-oriented programming essentially is interoperable with external software running on any platform, and it's easy to deploy as a Docker container, as we did in the project. So this concludes the first part of the presentation. Here, essentially, we have covered everything that is logic programming in the rush, and motivated why this is an interesting mechanism paradigm for attacking this problem in cybersecurity. So let's go ahead and begin seeing how this translates into the actual software architecture. So first of all, the background knowledge in our application is modeled as an ontology of different elements of the domain of cybersecurity in IIoT. And specifically what you're seeing here on screen is an excerpt of the portion relating to the relationship between attack actions and mitigation actions, and showing the links of mitigated by of which actions mitigate which others. So you can begin to see which are the options that can be employed under different circumstances. And this is an old version, but it was developed in conjunction with the project partners throughout the project. And we also drew inspiration from the Mitra attack matrix and Hindi's work from 2020. And the fundamental idea behind this is that since we can have a complex taxonomic representation in LogTalk, we could use this mechanism to build a complex ontology, which is essentially the taxonomy plus the cross-tree relationships directly within the logic programming system without needing other mechanisms like a semantic web reasoner or something of the sort. So now let's actually dive into the actual architecture of the application itself. So we'll go over it piece by piece, and we'll see how it all comes together as a single whole. So let's begin with the highest level view. So essentially, you have a constrained object-oriented logic programming as a service, as the guiding paradigm for everything we're doing. But there's a question of how do you actually manifest this as a software system you can use. And we did this through the essentially merging this this set of different extensions to logic programming in a single application independent inference engine. And essentially, this will allow us to have a declarative representation of everything that is needed, expose it through REST API, and allow interaction with the external world, all the while hiding all these details to the users and having these rich and complex decisions be transparent to the user. So how do we manifest it? Well, we manifest it through mixing these three important components on top of the Sweet Prolog runtime, which is the specific interpreter that we used for the project. We use the LogTalk runtime system. So we hook that on top of Sweet Prolog's compilation chain. To that, we add the constraint programming module. And then we also add the web server handling and creation mechanism. Then we essentially need to thread the execution together through all of them, and we'll see that in a second. And all together, they construct the Qup's inference engine. So essentially, within this this inference engine, since the public API for it is through REST, well, it essentially it contains its principal interface is the web API. Now, in terms of the implementation of what's inside the actual code, you have two different types of elements in the CuPy application. You have the objects I mentioned before, and then you have these mixins, which behave just like mixins in other languages. Essentially, you can create relations that are independent of any specific object, and then can be simply imported into others. So it's imagine just the drop-in replacement of additional code within your object. And this altogether builds the core part of the application. And there's of course a constraint logic programming statements within the implementation. So the application essentially begins by first taking in information through the constraint optimization problem generator. So it's a constraint satisfaction problem, but in addition has an optimization parameter that we use to decide between different options. Then it generates dynamically one of these problems, which is one of the innovations in some sense. Instead of having a static problem as is usually done in constraint programming, we actually build it dynamically. And we pass that to a solver. And from that solver, essentially, it constructs the corresponding representation of the mitigation actions that it needs. And then it wraps them up in JSON and sends them off to the visualization toolkit. So how does the optimization approach work? Simply put, as I said, we build a dynamic constraint optimization problem. How do we do this? We essentially build it in two steps. We take the attack action definitions. We use the ontology to enrich this information and get all the relationships to what mitigates it, what is the severity, and so on. And then you pass this dynamic problem to a solver, and it gives you back the solution that best satisfies the problem. And how do we specify the best solution? Well, we have a series of variables within our problem. Remember the definition I gave at the beginning of what a constraint satisfaction problem is? Well, here is the domains and the variables. So there are some Boolean decision variables, which essentially mean whether or not to pick a specific mitigation. And then there's some other parameters, which we call here R&B, which are essentially they're composite measures that we use to build the trade-off between having an attack, having a mitigation that is very severe on terms of business continuity against an attack that perhaps isn't very problematic and isn't very confident in its detection, or any other combination of these things. And then we build it all, and then we do this this equation, and then we optimize over this equation to rank the solutions. And essentially we look for all the satisfying assignments that in the order that they satisfy this optimization function. So essentially from here, our interest is in mainly making this fast and doing this efficiently. So we have two heuristics. We have one where we essentially say that the same mitigation for the same type of attack can always be done. It follows a little bit the idea that Jorgos was showing, where you can predefine some mitigations for some attacks in another portion of the project. Well, this is sort of the same idea, but applied to saying, well, if we have one type of attack, and then let's use the same optimal mitigation for all of them. And then we treat all the cases equally. And then there's a second heuristic where essentially we split the problem size into each specific asset. So if the assets have very complex multi-element attacks, then we just split it off for each asset, and this reduces the complexity of the problem. And we did some scalability experiments, but this is for the older version of the application, so it's probably not very representative today, but it had some very promising results in terms of speed up with the mitigation, because since it's a combinatorial problem, you will necessarily run into scalability issues once it really starts to kick in the exponential nature of it. So, but it works very well for problem sizes ranging up to 1,500. So it's more than adequate. So let's talk about briefly some of the related works that have been done, and with which we can compare our own approach. So basically, there's two types: those that also do many-to-many mappings from attacks to mitigations. There's this work from Kanun and continued by Samarji that do take into account pre and post conditions, but they only search from one mitigation, and they don't have a optimization criteria to select among the solutions. There's Vieira's work, which follows our ideas in a similar fashion, but they compute the utility. Their optimization function works differently. There's a González Granadillo's work that uses another complex optimization function, but they try to use a lot of real-world economic data which is not available in our case. And it uses another representation of they assume that there are static topologies, and they use pre-known topologies to calculate attack paths through the graph. There's a Nespoli's work which has another metaphor. It's based on the metaphor of the artificial immune system, and it essentially tries to modify mitigations to tailor them to the attacks, and to model how critical some assets may be based on their vulnerability status. But it unfortunately it requires a lot of data that may not necessarily be available. So it's very theoretical work. There are some other more limited mappings between attacks and mitigations done by these other works that I mentioned here quickly, and there's some that merely treat this as a mathematical exercise. So they do agree with our choice of mathematical formalism to tackle it. So to begin summarizing and closing off the presentation, the main contributions that I have presented are the mechanism to search for network reconfiguration actions that best mitigate a given attack, showed how that it is practical to construct these problems in an efficient way through the use of heuristics, showed that it is feasible and concise to implement these systems with logic programming, because it leads to very concise, short, and verifiable code. And we encapsulated this as a web service that is integrated into this larger cutting-edge C4IoT framework, which is a security orchestration framework for IoT networks. And I don't. And we have demonstrated its application on it through the project itself. Some limitations in future work that we're working on. There's some in simplicity in the attacks that we treat and the information that we get, but this is due to the missing spatial temporal relations. There's the output is itself also simple because it doesn't have these spatial temporal relations, but it's also due to the Sdn having abstracted away the entire view of the topology. But this is also something that can be integrated into a future version to follow some of the other papers that I mentioned. The mitigation choices are basically solely on the current attack set and not the past. There's some simplicity in the models. This bullet point, these numbers have changed, but the idea remains the same. And there's a single objective we're trying to maximize in our optimization problem. But in terms of future work, we wish to address this by having a more complex addition to the formalism that allows us to represent more complex spatial temporal information, and then to be able to really perform a far more fine-grained analysis of attacks. We also output temporal plans and use a more fine-grained probabilistic representation, and do this through the integration of two other orthogonal paradigms to this larger programming paradigm. And if possible, use adversarial machine learning to learn the rules for mitigations and relations between attack types and so on automatically, and to perform more realistic simulations. And with that, I conclude this presentation. I thank you all very much for listening, and if you have any questions, I am more than happy to take them. I think then we are done for today. We have covered the entire program schedule, and I wanted to thank each and every one of you for coming and participating, and especially say thanks to the presenters who did a great job all throughout the day and gave us some very, very interesting presentations that I think everyone here enjoyed.
Thank you very much for having us, Camilo. It was a very nice session.
It was a pleasure. It was a pleasure. I'm happy to see that it was a success and that people were happy to come. So it's always a good news when it works out well. So thank you all for making this possible and for participating. And thank you to the C4IoT project also. And with that, well, I guess I'll say good afternoon to everybody. And I hope I'll see you all soon and wish you all the best during this week.